Alright, hell yeah, let's do it. So we have Irodov, Problems in General Physics. Now this is by request. Someone's like, hey, 1.259, you know what I mean? Do it. And, you know what I mean? So, hell yeah. And this is right up my alley right now because as of last month, I didn't know how to do rotation. And the only way I'm going to teach you how to do rotational problems is if you know what the hell's going on. You know what I mean? If I had no idea what was going on and someone said, hey, could you do an electrical engineering problem? I would cheat. I would go to the solution, and then I would just see what numbers are being multiplied. You know what I mean? That can be your first step in life, to be like, okay, I have a mass A, and then I have these radiuses. Well, I'm sure I multiply some of the radiuses and some of the masses, you know what I mean, maybe by a half. You know, you get it, you know what I mean? But your knowledge, you know, you're not going to learn anything. So what we do, speaking in the third person, is you have to simplify it, you know what I mean? So do every problem except this problem, but you know, work towards it. So and this will be pretty sweet. So we have this arrangement. What does it say? And sometimes just go to the question first. It says find the acceleration of A. Sweet. After it's held and then let go. All right, settle down. So anyway, so the simplest thing to do is take this mass A and drop it off a cliff. All right, so hell yeah, that's mass, and that's mass A. And here's our cliff, and here's our puddle of water. Okay, so what's the acceleration of this? And maybe the acceleration will change. Who knows? But all we're asking for is the acceleration at this moment. You know what I mean? Because some problems, hey, this thing might be oblong. You know what I mean? And so maybe the acceleration is going to change. And sometimes, you know what I mean, you can even take those problems and make them simpler, especially when they're just like, hey, well, what's the acceleration right here? So if we figure out, and now this is basic, but you should not understate it. We have to use F equals ma. So what this says is that if we have a mass, and let's do our free body diagram. Because what we do is we chop some sort of mass, so like right here, and we'll do this one first. We chop it and then just throw it into the deepest reaches of space, and then go back and forth between your problem and this mass in deep space. So if we go to our problem, and this F equals ma, I do eyeballs on this side, textbook on this side. So eyeballs means that, hey, is this going to move? Like, do we see motion? If we set this experiment up, you know what I mean? Hell yeah, this thing's going to fall. It's going to start moving. Well, we're going to say, hey, and it does. It has an initial velocity, like v naught, of 0. And then 1 second later, guess what? It's going to have a velocity at t is equal to 1 second. Why? Because we're trying to find the acceleration. And the acceleration will be change in velocity, change in time, and it'll probably have units of like meters per second. Sweet. And so it's totally spelled out that in 1 second, this thing's going to go from 0 to whatever. And so we'll do that with this one. And then we'll use those basics. Because kind of the foreshadow is like, okay, so we're trying to simplify this part. Let's simplify this part. Don't hang the mass, and then just have this thing. You know what I mean? Oh. Never mind. Oh, this is a hell of a hard problem. I thought this was just held and then rotating. Because my first go, that's so cool. Because my first go-to was like, hey, look at this. If this is supported by the axle, like, is it going to move? It's like, no. So don't you take away the mass, and then if this is supported by the axle, you know what I mean, is this stationary? Hell yeah. But oh hell no. Not in the formation that it's in. So we got a couple things going on here. If we get rid of the mass, oh, this thing's going to, it's like holding on to the toilet paper side of a roll of toilet paper, and away it goes. You know what I mean? So we might have a doozy in front of us, and we'll see if we can even do it. All right, but might as well start at the basics. Is you know, if we're so yeah, we do see some acceleration, and then so what this F equals ma says is that if we do see acceleration, whoa, let's slow down. So yes, so this is going to be some number. And then we go over here. It's just like, well, if we do have a mass and we do have a change in velocity, you must have a force. So like, let's say we see a change in velocity in this direction. It's like the y direction. And we're observing a mass and we see it changing its velocity. It has to have a force in the y direction. There's no other way to get anything to move in the known universe. And I don't know, you know what I mean, I think you should think of it like that, but it's almost like this equation like kind of describes it as so, you know what I mean. But I mean, from all Newtonian purposes, it's just like, yeah, we kind of understand this concept of force, you know what I mean. Like even though it's a little bit elusive. You know what I mean? We know that the mass is changing velocity, and then we just, you know, setting this equal to the force causing that, like F equals ma, was groundbreaking, you know what I mean? And we set it to be so. So I don't want to get too esoteric, but hell yeah. So so if we have some acceleration, we must have a force in that direction. And what force do we have? Well, we have the force of gravity. And this is where you should write it like Kepler. You know what I mean? Hey, that's a gravitational constant, the mass that we're trying to analyze, mass of the Earth's radius of the Earth squared. Cool, so this goes in this side of the equation. You know what I mean? I think you should always do this every time for every problem. So we have this. So we're doing F equals ma, and so this was our force, and then we have the mass times acceleration. Now, maybe you have a strong wind blowing up. You know what I mean? You have the force of the wind. Well, that's going in the other direction. So, hey, you have this force going down, and then maybe you subtract it with the force of the wind. And that's some function of the wind's velocity of the wind. I don't know, you know what I mean, and the actual, and maybe it's like the actual velocity of the wind plus the velocity of the mass, you know what I mean, the actual velocity of the mass, you know what I mean, that would get hella complicated, you know, but anyway, so all we have is the force of gravity is equal to the mass that we're analyzing and its acceleration, the number we're trying to find. Cool. This stuff in Kepler's equation is just g, so you just have mg is equal to ma. And sometimes this gets a little confusing because it looks like this side is that side, but mainly just for this, because we say it so, you know what I mean? This g is the acceleration of gravity, and so it's just the way we write it. But I swear, the fact that this side looks like that side, and you're supposed to put this into that side of the equation, it seems a little bit funky. But anyway, so now you're just going to solve for a, and we have mg divided by m, and that's just going to be g. So our acceleration in this case is just gravity. Cool. All right, so now we are totally going to solve this problem first. It's just like, hey, we're going to fix an axle, and this is the problem that we're going to solve first. All right, and maybe, you know what I mean, maybe at this point I'm just like, you know, just not even, just balking, you know what I mean, it's like, but no, we'll get there, we'll get there. Now, one aspect of a force with F equals ma is like, hey, if you have a, like, even with gravity, hey, we say this, we have a force of gravity, and we simplify it, that force is mg. So, okay, so it's the mass times gravity. Now, this isn't a quantity of newtons, and so I just turn everything into 1 kilogram, you know what I mean? Because if I have a mass m, and it's like one of the only, and you can do it with both things. You know, we can say a pulley B, we can say this whole assembly has a mass of 1 kilogram, and this weight has a mass of 1 kilogram. You know what I mean? Hey, cool. Alright, so, but yeah, so if this is a mass of 1, gravity, we're just going to use gravity as 10 meters per second squared, you know what I mean, not 9.8, we got enough things to worry about, you know what I mean, it's kind of just nice to simplify that to 10, And then you can go back and hone in your answer a little bit more and change this to like 9.8 or do whatever you want, 9.81. Okay, but that force of gravity is going to be 1 times 10. That's going to be 10 newtons. All right, so we have this idea that we have a 10 Newton force on this mass. Now, and that's the same thing as going to an icy lake down here. Well, I guess we'll put the icy lake right here. And then we're gonna pull, you know, I mean, maybe with a little bit of rope, and then one of those springs that you get at the hardware store that measures force. And we're like a fish scale, you know. So it's gonna read 10 pounds, and we're gonna pull on this thing so it always reads 10 pounds. You know what I mean? That's the same thing that's gonna happen here. And I think for a lot of problems, it's best just to think in 1 second intervals. So we found the acceleration, and what does this say? It says that this is 10 meters per second squared. Don't write it like that. Write it like this: 10 meters per second. And you can even say 1 second, and you can put bells and whistles on it. It's the change in velocity of 10 meters per second and then you can say every 1 second. So we're just going to work in 1 second intervals. We jumped off a cliff, we're going 0 velocity, or we just threw this 1 kilogram mass, couple pounds. It's got 0 velocity, but 1 second later, because it has an acceleration, we are going to change our velocity to 10. So at time is equal to 1 second, our velocity now is 10 meters per second. Now here is where you got to do that quick calculus in your head. Did we go 10 meters per second for that whole second? Hell no. We started out at 0. And this stuff doesn't come up a lot. You know what I mean? I always do the scenario of this, but it's nonsensical. You know what I mean? Hey, we're gonna make our car go from 0 to 60 miles per hour. And we're gonna do this over the course of 1 hour, let's say. You know what I mean? So in 1 hour, so we're going to go from 0 to 60. And the question is maybe what was our average velocity average, and maybe what was our distance that we traveled. Those are the two questions we want to know. And so if we started out at 0, well, we weren't going 0 the entire time. We weren't going 60 the entire time. So this strategy actually is really good. You know what I mean? Because you're just like, well, maybe my average velocity is 0 miles per hour. Maybe my average velocity is 60 miles per hour. You know what I mean? Maybe it's just one of those. You know what I mean? And hey, you just narrowed it down out of all the numbers in the known universe. Hey, you did pretty good there. You know what I mean? You got it between, you know, the velocity is either going to be 0 or 60. It can't be any other number. You know what I mean? It can't be 120. That would be nonsensical. So even right there, pat yourself on the back. But anyway, so yeah, same thing here. If we're 0 velocity here, and then 10 meters per second a second later, well, what was our average velocity? And don't think things, you know what I mean? Some problems are totally linear and you don't even realize. I just did one of these Irodov with friction, and it was just like, oh no, friction, yeah, someone's just like, yeah, friction's just linear. And so, you know what I mean? And once you recognize that, you know, this velocity, I'm not doing this. I'm not like increasing my velocity right at the very end or something. And then, yeah, the average velocity would be kind of the center of mass of this graph. It would be, well, no, hell no, it's not so. I'm just making up stuff now. But yeah, because if we have a triangle, hell no. So anyway, so it's just that halfway point. Yeah, so our average velocity is just the halfway. In this case, we're going average velocity of 30 miles per hour, and we did that for an hour. Hey, cool, we went 30 miles. For this, our average velocity is halfway between 0 and 10, so our average velocity is 5 meter, and we're doing meters per second here. And just to check on reality, gravity, this is 22 miles per hour. So gravity is going to be 22 miles per hour per every second. Every second, you're going to increase your velocity by 22 miles an hour. So cool. And maybe it's like 22.2. You know, that's probably a pretty darn good accurate number there. Anyway, okay, so how far did we go in this case? Hey, we were going 5 meters per second for 1 second. We went 5 meters. So cool. So this distance is 5 meters. Alright, hell yeah. So now I think it's really good for our brains to be able to like turn gravity on and off. You know what I mean? So let's say I turn gravity on for 1 second. You jump off a cliff, now you're going 5 meters per second. You're going about 10 miles an hour. That's pretty sweet. And then let's say gravity just got turned off, and then you get to fall the rest of the way off your I don't know, 15-meter cliff, you know what I mean, whatever. You know, at a nice cruising speed of 10 miles an hour, you know what I mean, 5 meters per second. That would be pretty sweet. No, excuse me. No, hell no. In 1 second, our velocity is actually 10 meters per second. And I shouldn't do these with double numbers because it gets confusing. But yeah, we'll just stick to, yeah, 10 meters per second is 22. You can do that mental math in your head, but we got to focus on meters per second. So yeah, let's say you could turn gravity on for a second and then shut it off. You'd be going 10 meters per second, and then you'd be continuing that speed. And for the sake of a cliff, your free fall is only going to be about 2 seconds. You know, if it's like a 40, 50-foot cliff, 2 seconds of free fall, you're going to be going 20 meters per second. You can do the mental math of that's 40 miles an hour, let's say. But anyway, but if you can turn gravity off after a second, you'll just continue going that speed. All right, so that scenario might not be useful, but I think that is a useful concept just mentally. Like, hey, let's turn on this force and then turn it off. And if I turn off the force, hey, there is no more net force, and then our acceleration is no more. But we still maintain our velocity. Cool. Because what we're getting at is this next thing. Let's say I got two rocks or two masses, and I just like just kind of drop them off. They're right there, and they're ready to go down this cliff. Now, and then for whatever reason, I can channel the gravity like right here, but then there is no gravity on this side. Cool. So now let's say we have this. Okay, and if this is the case, gravity is just normal on this side, and we're going to say, hey, this is 1 kilogram and this is 1 kilogram. And so same thing applies to this one. You know what I mean? Hey, we go 5 meters, and in 1 second we're going 10 meters per second. Now there is no force of gravity. We were able to turn gravity off over here, and this one is just after a second. It's in the same location. V naught is 0 meters per second, and the velocity at t1 is 0 meters per second. You know what I mean? And so so now the scenario is that I guess I'll draw it over here. Now, let's say these two chunks of mass are actually connected, and I'm going to still do a square, and so here's how they're connected. This is a and we'll do 0.5. No, we'll do 1. So this chunk, this half is 1 kilogram, and this half is 1 kilogram. But for whatever reason, we can get gravity to work on this side and not on that side. Okay, but this mass is still connected to itself. You know what I mean? And we're going to say, hey, this is fairly narrow, where we're going to neglect that it spins. You know what I mean? So for this scenario, it's like we have, and then it is good to do these, you know what I mean? Hey, this is a point mass, and we're going to put another point mass right next to it and attach 2 point masses together, but they still occupy kind of the same space. And we're going to say the force of gravity works on one of those point masses, but not on the other. Now, I think this is a very important. And what's the foreshadow here? The foreshadow here is we have something that's going to so back to this scenario. If we do have an axle here and it's supported by that axle, I think this is the simpler problem to do. And then you drop this mass. If you get rid of the mass, there is no movement of this assembly. It doesn't move up or down, and it doesn't spin. But now you have you have applied a mass over here, and so when gravity, so now we have, it's just like you're turning on gravity just over this little chunk of mass, but for all purposes, like you're turning off gravity above this. You know what I mean? It wouldn't matter in this case if this thing was just hovering in outer space. And this is cool. I called my brother the other day, and I think this is channeled from that conversation. You know what I mean? Because even that, you're just like, what? It doesn't matter if this thing's just floating in outer space? No, it doesn't. You know what I mean? Because we have a force, a normal force up, you know, on these supports, and we do have a force of gravity acting through the center of mass, but those are balanced. And so if we did the free body diagram on this, we take this object and then put it into deep space. You know what I mean? What do we observe? And then let's get rid of the mass. You know what I mean? So and then we're just supporting it through the axle. So if we do F equals ma, you know what I mean, what do we notice? What's the eyeballs on acceleration? There is none. It is 0. Well, that must mean that So this is how I do F equals ma. So if I know, because this is bizarre actually. It's bizarre to have something not move actually, you know what I mean? But we design bridges and we design buildings, and hell no, we don't want them to move. But from an F equals ma perspective, it's fascinating, you know, that things just don't move all the time. Because we observe that the bridge or this or the building doesn't move, and then so, but then we go to this side, and it's like, well, don't we, because when I do free body diagrams, and I think this is a really cool way to do it, let's take this object and throw it into deep space where there is no stars. You know what I mean? There is no gravity. It's in a separate universe all alone. You know what I mean? And, so, yeah. And it's just there. And then we're gonna, but it has all the same properties that it has on Earth. So, if we don't see it moving on Earth, we don't see it moving, you know, in that deep space scenario. But then when we go back to Earth, we know that we have an Earth underneath us, and this is made out of that big little m, the big M mass, big M. And because the mass of the Earth and the mass of this, we know that because of Kepler's equation, there is going to be a force. You know what I mean? So there's going to be a attractive force. There's going to be a force, basically it would look like this, a force down on this through the center of mass. So then go over here to your diagram in deep space and put that force on there. Okay, but so you identified one force, but you had no movement. So you can't. Definitionally, it says if you have a force and identified even one force, then this mass that you're free body diagramming, throwing in outer space, is going to change its velocity. But we don't see that. So how can it be? You know what I mean? And then just to spell it out is like Newton's, I forget if it's second law, but you have to have a force to counteract this. So we're just going to say, well, that this is going to be, we're going to have a force on this axle. So we're going to say this is like axle A, this is a B, and so these are upward forces on those. So we have, so here on our free body diagram, we have this force and that force, and so we have an AY and a BY. And so those are the forces. We have a force down and these two forces up, and they balance. You know what I mean? A plus B is equal to that force of gravity. Sweet. And so, so hell yeah, we did it. And, oh, now I got to relate it to how this is the only driver. How you can basically say there's no force of gravity on this, it wouldn't matter, but there is a force of gravity isolated on this. Alright, so that, hell yeah, that whole tangent was just to be like, okay, so we have this idea that we can maybe, like, beam the force right here. The force of gravity works on this, but it's not on that. And this is really important, because it shows the concept that if, so F equals ma, let's write it again. So it says, hey, if we're identifying a mass, and then we identify a force on that mass. So, and let's just put this block in deep space. So this is kind of the deep space scenario. And then I think it gets confusing when your forces are up and down just because we're so used to gravity. So it's cool to do in deep space, throw a force sideways. You know what I mean? So if I have a force sideways, then I by definition, I'm going to experience a number for acceleration. And that's going to say a change in velocity, change in time. And if this thing is not moving at time 1 second later, it's going to be moving whatever this number was, if the units are meters per second per second. You know what I mean? I guess you could change the units to something bizarre, like a change in velocity of meters per second per hour. You know what I mean? But typically, we'll do meters per second squared, and if you write it like this, it's just a little bit more forgiving. You know what I mean? Or it's just a little, it's more explanatory. Okay, so the foreshadow here is that we're going to identify that, hell yeah, we're so used to the force of gravity. You know what I mean? If this is 1 kilogram, the force of gravity is mg. That's going to be 1 kilogram times 10 meters per second squared, and that's going to be 10 newtons. So we're so used to this that because we jump off a cliff, we're experiencing the same thing every time. We can't. You know, gravity is not one thing one day and one thing the other. It'd be cool if it was. Like, it'd be way sweet if, like, the moon was overhead and then we all started floating around for a while. You know what I mean? That would be rad. But anyway, gravity of the moon isn't very strong. Okay, so, I guess what I'm getting at is you could, so you have to get into your, like, well, I don't know. I guess the idea is that, hey, we have a 10 Newton force on this 1 kilogram. We experience that as free fall. That is a great example to go to. But let's say I just have a 5 Newton force on this same 1 kilogram. Like, now what's going to happen? So we go back to our F equals ma. Here, I had a force of 10, and then it's always good. Anytime you have an equation, you should always probably write it as many ways as you can. So let's do that right now. So we have F equals ma. We can write it like this. Let's write it the other classic way and say, hey, if we solve for acceleration, the mass goes downstairs. So we have force over mass. And can we get something else? You know what I mean? You could even get mass is equal to force divided by acceleration. Probably one that doesn't, I can't even talk about that one right now, but I'm sure it just makes logical sense. Anyway, but here's your two players, you know what I mean? Hey, if we identify the forces, and there is a net force, and then we find, and we divide it by our mass that we're observing, that is going to be the number for acceleration. So the acceleration for gravity was 10. Because we have a 10, it's only, the acceleration of gravity is 10. And that's where I think this mg is equal to ma is such a disaster, because because you have this, acceleration is gravity, and you know what I mean, it's like, you just solve for acceleration. It's just a number, man. And it's the number in this scenario where you jumped off a cliff. In physics, you're going to have to be so many different scenarios. And even here, you jump off the cliff and you fall for more than 10 seconds. Well, hell yeah, you're going to have force of drag, so your acceleration isn't going to be g. So I think there's just too much emphasis, you know what I mean? I think yeah, here's my thought on physics in general. Some numbers, and I'll even chalk this up with g. The fact that you even label it makes people misunderstand the fundamentals of what's going on. So I'm just going to label some like pi, e, I don't know, even from material mechanics, this epsilon, you know what I mean, strain, like holy Toledo. I think just the letter itself, you know what I mean, spells out that you're going to have a hard time in the class, you know what I mean. So, and it doesn't have to be, you know what I mean. Hey, pi is 3. This is, you could round down to 2. It's not 2, it's 2.7. But anyway, you just call them both 3. You know what I mean. But yeah. Alright, so that was a little bit of a tangent, but yeah, we have to identify. So what we're doing is we're saying, shoot, yeah, we can have a 5 Newton force on this, and what's going to happen? Well, our acceleration is going to be, because that's where I said, like, hey, isn't this g right there? Well, no. Like, yes. No. You know what I mean? It's, holy hell. It's, let me pause the camera for this. Alright, hell yeah. So here's my little rant on F equals ma when it comes to gravity. So yeah, we F equals ma is king, and then we say that the force of gravity, yeah, and sometimes, like, hell yeah, when we jump off a cliff. Alright, hell yeah, so we're back. Had to get some more juice and stuff. Alright, so yeah, if we jump off a cliff, F equals ma has a textbook side and an emotion side. You know what I mean? It's always good to run an experiment. Hey, we have some sort of mass. It had 0 velocity, and then all of a sudden has some velocity. You know what I mean? Cool. Check on reality that we have acceleration. I wouldn't get too focused on that side of the equation. Let's see. Well, you know, if you're doing, well, there's two sides to focus on for sure. Because if you're doing like rotational stuff, hell yeah, you want to know. And if I got a stopwatch and a speed gun, you know what I mean? Hey, I can focus on this side as much as I want, you know, because it's a change in velocity, change in time. Hell yeah, if I can get numbers on those, then I'm just set. I know what this side of the equation is. And so definitionally, I would know that this side has to equal that side. Alright, but the other thing is to just focus on the force side. There's only so many things in the known universe that cause force. And one of just having mass and then something else like the Earth having another mass is one of the classic ones, you know what I mean, that will generate a force. So we can say this side of the equation, you have a force of gravity. Now this side of the equation is still like, hell yeah, like this is the mass that we're analyzing, and we want to know its number for its change in velocity. Like typically that's exactly what we want. We want to solve for acceleration usually. Okay, so due to Kepler, we have an equation for the force between two objects, you know what I mean? And so it's this gravitational force. It's a gravitational constant, the mass that we're analyzing, and so you know, those two are the same. And then mass of the Earth divided by the radius of the Earth squared. So we throw that into this side of the equation, and then we say that's equal to the mass we're analyzing times acceleration. It just happens to be that this equation is a function of mass. You know what I mean? It didn't have to be. It could just be a function of your location. You know what I mean? And so if it was a function of just your location, well then what? Yeah. So quickly, you know what I mean? What this would say, if the force is just a function of the mass of the Earth, and then your location away from that mass, and this gravitational constant. So when we go to analyze F equals ma, hey, this number is just going to be a constant. You know what I mean? Hey, a constant number, and then but this will change. So let's say we have a mass of 1 kilogram. Well, what we really want is to solve for acceleration. So in that case, our acceleration will be this constant number. I didn't mean to write it downstairs, but hell yeah. Constant number, and then we just divide by mass. So if we divide by 1 kilogram, hell yeah. So we have a check that this is going to be, whatever this constant number is going to be, our change in velocity. Now, if our mass is 1. But let's say something has heavier mass, you know what I mean, 100 kilograms, you know what I mean, that could be a person. And so what would be our acceleration? Our acceleration in that case would be this constant number divided by 100. Whoa, that would be trippy. That if you weighed more, then you would jump off a cliff and go slower. Oh, that would be rad. Now it's just like, and so this is such a good, I think I'm blowing like my mind, and maybe others. You're just like, oh, I never thought of that. I never, you know, and this is a Vertasium. He goes around asking people like, hey, like, is there more force on a heavy-ass bowling ball compared to like a tennis ball dropped at the same height? We know they pick up speed the same, but the only way to get that heavy-ass mass to change its velocity, so let's go back to F equals ma. The only way we're going to get that change in velocity to be the F equals little m, you know what I mean, this little mass, a, to get these things to be the same, this is a tiny mass, so it must have a, and this is a hell of a large mass. And, what were we doing? Oh yeah, and this number is going to be the same. Well, look at this. This is going to have way less force. You know what I mean? You know, so this force is going to be tiny, and to get this, to make this equal, if I have a big number here and then a big mass, well, this force must be hella big, and so that's what we see in reality. You have a huge mass. Well, you must generate a huge force, and it just happens to be that the force of gravity has that functioned in. You know what I mean? The equation does, where yeah, it's proportional. You know what I mean? So if you have a bigger mass, it's going to put more force on that. But at the end of the day, these masses, when we do F equals ma, you can see that acceleration isn't a function of mass. You know what I mean? Hey, both these masses, one big, one small, are still in 1 second going to change velocity, so the velocities will be the same, and the distance they travel after 1 second will be the same. Cool. But hella force to do this. Because now we're going to get into the scenario, kind of back at it, of just like, well, could we have a mass, chop it in two, and only have gravity on one side of it, where the other side doesn't have that force? Yeah, so that's kind of where we're going. And the huge foreshadow for this is like, hey, we have a driver, you know what I mean? We have a force on this mass that's going to be pulling down, and we're still having this in the axial position. But this mass is causing other masses to move. You know what I mean? So then it's going to be slower. And I do have to draw this one, because sometimes when you're studying physics, you're just like, oh, my mind is melting, and I don't see it. So this is the one where it's just like, oh, this one gets me, it got me like revisiting physics and stuff. Let's say I have 100 kilograms here and 50 kilograms here. And I wanted to draw it the other way, but, you know, you could make the, and I was making this assumption, it's just like, well, isn't it just 100 minus 50? Isn't that the same thing as having 50 kilograms in free fall? Like it jumped off a cliff? And, like, you'd want to play around with this idea. You know what I mean? Grab a pulley, have two weights, you know, drop something in free fall. You know, drop something that weighs, you know, do this, and then drop something that weighs twice as much, you know, 100 kilograms in free fall, and then clock them. You know, obviously they're going to land at the same time. We just covered that. And so you're just like, well, what gives here? And so let's talk about this one, because this problem is very I think is very similar to like mentally of what's going on in this scenario. Okay, so with pulley problems, what I like to do is like stretch out the cord and just kind of put it on a flat surface, or again just in outer space. And so we have this 100 kilogram and then this 50 kilogram and then a rope between them. And then we go back to the problem, and then we got two drivers. You know, the force of gravity is going to work on both of these. You know what I mean? For this scenario, we don't have to just chop, we don't have to say the force of gravity isn't. It is working on both of these. And the force of gravity is the mass times g. Well, we'll go back to it. Yeah, g is just a number. It's 10. You know, I mean, sometimes it might be better just to write 10. The force of gravity, and we're going to call this mass A, mass B. So we have mass A times G, and then we have mass B. Let's try this out. Mass B times 10. You know what I mean? Cool. So, yeah, let's literally try. The force of gravity is going to be 10 mass A, and then the force of gravity over here is going to be 10 mass B. But we know that mass A is 100, so the force of gravity is 10 times 100, which is 1,000. And the force of gravity over here is 10 times 50, which is 500. So now we have a force down of 500 and a force down of 1,000. You know what I mean? So if we do those, and so if we choose the y direction, and you can put it this way. Hey, we have a force this way of 1,000 newtons, and then we have a force this way of 500 newtons. And now you can see that we have a total force going that way of 500 newtons. You know, you can just cross that one out and say this is 500 newtons that way. All right, so now since we put this problem like on a slippery surface or just better in outer space, we still have the masses just sitting there in outer space, and now we're only putting a 500 Newton. So this is where, you know what I mean, you just want to use gravity as an actual number and not get too carried away with the letterage of it. So yeah, and we're going to come back here to F equals ma. And when we do this, now you know, both these masses are like connected. You know what I mean? Like just because one mass is over here and then we have like a rope or a string in the other mass, you know what I mean? We're not, nothing's funny is going on. It was like we're just applying constant tension. So like continuity will be followed. It would be the same thing as drawing this as like a slender rod to a 50, you know what I mean? Because then, and this would just be called a rigid body, and I'm trying to get better at the kind of just using the terminology. It's just like, hell yeah, if this is just a rigid structure, you could just say it looks like that, you know what I mean? And so what we're getting at is that the total mass of this, for this scenario, is 150. But then that's the mass. We want to know the acceleration. The only driver is 500 newtons. And so back to the scenario where I just thought this was 100 minus 50. Well, what would be the force of gravity on a 50 kilogram mass? That would be, the force would be 50 times 10. That would be 500 newtons. Cool, but we have that 500 newtons not just on 50 kilograms. We have that 500 newtons on 150. So here our acceleration is going to be gravity's 10, but here our acceleration is going to be 500 newtons divided by 150 kilograms. And there's another thing to bring up is like the units on F equals ma. Always good to write the units. You can do it like this or whatever, or do it like this. This is for units, and then we have Newton is a kilogram, and then a meter per second squared. You know what I mean? And you can even write it like 1 Newton is equal to 1 kilogram moving at 1 meter per second. And let's do it creatively. There you go. Per second. There you go. Cool. And you can even write another 1 down there if you wanted to. Okay, hell yeah. But this is so cool because now we only have a 500 Newton force. You know, I mean, we don't have 1,000. And cool. I think we observed that, hell yeah. Like I just wanted to say, hey, isn't this the same as just a 50 kilogram Newton in free fall? Well, sure, you'd have a 500 Newton force, but it wouldn't just be on that. It's on the whole system. So that whole system is 150. So back to this. We have 500 newtons divided by 150, and our acceleration is 3.3. And you really should do this problem where, hell yeah, one mass is twice the other, and then you're always going to get this. So this is such a classic problem. Every physics problem can be a check on reality. But yeah, this one, you know, for sure. So now my acceleration of the whole system is just 3.3. So yeah. And now the question is, why is that? So I mean, because now we can do the same scenario even sideways. Let's say we have this 100 kilograms, and then we have 50 kilograms, and then we're going to say, hey, we can have this force of gravity sideways, and we can turn it on or off. And then for this 50 kilogram, we're going to turn it off. But on this 100 kilogram, we're going to turn it on. The force of gravity is going to be on, and we know that force of gravity to be mg, or just mass times 10. And so this is going to be 100 times 10. That's going to be 1,000 newtons. Cool. And so now we have this scenario, and we can call this a string, or we can just make the rigid body. But now we have, and then let's do both of these. So we have we don't have a string here, and this one is just a 50 kilogram just floating in outer space. We don't put a force on this one. This stays stationary. But then we put 1,000 Newton force on this one, and hell yeah, F equals ma. we put 1,000 Newton force is equal to 100 kilograms. What's our acceleration? It's going to be 10. You know what I mean? We just did it in reverse. So if these are not connected, and we can turn off gravity on this one and turn on gravity on this one, hell yeah, this one's going to be moving 10 meters per second every 1 second. But if we're able to turn off gravity in this scenario, and these things are connected, but we can turn on the force of gravity for this mass, what happens is this mass has to pull that mass. So the total mass is what's happening. So F equals ma. Sometimes you do mass total right here. We only have a driving force of 1,000 newtons. We have a total mass of 150. And then we want to find our acceleration. It's 3.33. But that was just another way to explain it, you know, real fast, where it's like you don't even have to do the pulley problem. This pulley problem really helps, but you can just I think this is a very good thing to do, where you have the scenario, and we're going to come back to this one and do that same thing. All right, hell yeah! So we're almost kind of done with this section, because this was kind of the introduction of like, hey, we have a driving force that is going to operate on this mass. Don't get me wrong. And if this is in free fall, hell yeah, we're going to see that 10 meters per second every second. But it's not. The same force is operating on the whole mass. And just because this thing is going to be rotating, that's the other, you know what I mean? I think the second simplest scenario to be like, hey, how can we make this thing look where it doesn't look just awful? You do this. So here's mass A. And then you're going to have a pulley. And then you're just going to have another mass on a frictionless icy surface. Cool. And then so this is mass B. And then we can do that same scenario where, you know what I mean, this is 100 kilograms and this is 50 kilograms. We have that driving force of gravity. Hey, we don't have the force of gravity this way. It is nothing. You know what I mean? So it's the same scenario. And now let's get back to the way I want to do it. So heck yeah, so we're going to have this 100 kilograms, and it's going to actually be attached to a 50 kilogram. So we have 100 kilograms, and then we can just say, I can turn on gravity right here, you know what I mean? But for whatever reason, I can put a little shield where there is going to be no gravity over here. So this force of gravity is going to be 100 newtons. But now if we use F equals ma, you know, it's very obvious that we have that 1,000 Newton driving force. The whole mass, though, is 150, and we can find the acceleration, and that's going to be 3.3. And we can do the same thing. If these aren't connected, well, hell yeah, you know, if they're just next to each other, but we can turn off the force. Hey, this one's going to go 5 meters in 1 second, so it's going to be down here, and this one's just going to stay put. Now, let's, for the sake of argument, figure out how far this one went. You always want to be able to do that, like just 1 second interval. So we're going to say this whole system moves, the velocity goes from 0 to 3.3. That's the acceleration. Definitionally, it says this is going to change in velocity by 3.3 meters per second. So now after a second, it's going to go 3.3. Again, what's the average velocity? Now you can just do it in your head. It's just going to be halfway, 0 to 3.3. Just guess, it's like 1.5. If I wanted to guess more, it's like 1.515. You know what I mean? Hey, we're doing pretty good. 1.5. Sorry, 1.5. 1.515. Is that right? Divided by 2. No, I was way off. No, duh. Yeah, 1.6 repeat. Cool. Yeah, so that's going to be our average velocity, meters per second, and we went that far in a second, you know, and we traveled that speed, that average velocity, for 1 second, so we went 1.6 repeat meters. So here, if gravity was all on, you know what I mean, hell yeah, we go 5 meters, but here we're only going to go 1.6, you know what I mean, so just a third of gravity really reduces that. Now is 5 divided by, because 10 divided by 3.3 is a factor of 3. 5 divided by 3, hell yeah, so it's a linear relationship, you know what I mean? So if gravity is a third, I'm going a third of the distance. So instead of 5, I'm going 5 divided by 3, I'm going that 1.6. See, that's a scenario where I had to catch myself. I was just like, oh, maybe it's not linear. So anytime you can find a linear relationship, double down and just be like, hey, you know, prove that it's linear, because that'll make your mind not melt, and just be like, cool. You know what I mean? Then I can just visually see it. If acceleration of gravity is, and then don't say the acceleration of gravity. That's where it's just like F equals ma. You're just finding the acceleration of the system. You know what I mean? We're identifying that the whole mass of the system is what we want to identify. We've identified the forces on that mass, and we're finding the acceleration. If the acceleration just happens to be 10, you know what I mean? Cool. Like, just, you know, nod your head and note that. But yeah. So, because I think fundamentally, like, you can relate it. You can say that 3.3 is 10 divided by 3. You know, it's a third of gravity. You know what I mean? So, but it's just 3. It's just 3.3. It's just the acceleration. Who cares what it's related to gravity? You know what I mean? I guess the only time you want to relate it to gravity, sometimes it's just like, hey, the human body can only take 5 Gs, 5 to 6 Gs for a few seconds. So if you're building roller coasters and you're generating 10 Gs, you might kill people. You know what I mean? So that would be 100 meters per second. You know, if you go to 0 to 200 miles an hour in a second, well, hell yeah, that person's dead. Oh, sweet. Even a comment like that is just like, oh, you go from 0 to 200 miles per hour in a second, you're dead. You know, but maybe, you know, that you're experiencing an acceleration of gravity that might be at a human limit. 10 might be able to sustain for a very short fraction of a time. But let's say you're driving 100 miles per hour and you run into a brick wall, but you want all your safety features like your airbags. The only way you're going to survive is if you're, because, you know, you can barely survive a change of speed of 100 to 200 miles an hour to 0 in 1 second. So you can't have 100 miles per hour to 0 in a half of a second. So if it's 0.5 seconds, so you need airbags to cushion your blow. So once that thing impacts, and like it might not be theoretically possible, because check this out. Like we could even do this one right here. It's very fascinating because it's a momentum problem. Like what's the distance between the front of the car and you? You know what I mean? So if you're in the car, what do you think? It's not a 4x8 sheet of plywood. Maybe. You know what I mean? Let's give it the benefit of the doubt. And let's not. Well, yeah. I don't know. Well, let's say it's 2 meters. There you go. Because we're going to be in meters anyway, I think. And 100 miles an hour, that's going to be 100 divided by 2.25. It's 44. It's going to be 45 meters per second. So we're going to go 45 meters per second. And so our velocity is 45 meters per second. We're going velocity 0. And so we have a change in velocity of 45 meters per second. And it can't be more than a half a second, so 0.5. So 0.5 seconds. So our acceleration can't be more than, 45 divided by 0.5. Yeah, our acceleration can't be more than 90. You know, we were thinking 100, but here you go. So, let's say you can go 50 meters. So we'll go 50 meters per second divided by 0.5, and that's going to be that 100 meters per second squared. Your acceleration can't be more than that. So now the question is, how far did you go? So if I went from 0 to 100 meters per second in a fraction of a half of a second, what was my average velocity? Well, my average velocity was 50 meters per second, and I did this for a half of a second. You know what I mean? So even though, you know, the numbers are kind of different, it's the same thing as, like, you know, miles per hour. If I was going 60 miles per hour for 1 hour, I went 60 miles. If I went 60 miles per hour for 0.5 hours, I went 30 miles. So here we're going 50 meters per second for a half of a second, 0.5 seconds. So cool. So we're going to go 25 meters. So we need 25 meters of stopping distance to not generate 10 Gs. So now I think the human body probably for an instant can experience a shock load of more than 10 Gs, because like, unless I'm doing the problem wrong, you know what I mean? Because let's figure this out. Like, let's say you do totally crunch the front end of your car, the airbag explodes, and we have a crunch zone of 1 meter. You know, I think that's fairly decent. That would be a fairly heavy accident. Okay, so how do we do this problem in reverse? Yeah. And I'll have to think about this. All right, I kind of thought about it. And so we're going to do like a sane crash. Like, you know, I don't know what's sane at all. But 50 miles an hour? 50 divided by 2.25, that's like 20. How about 20 meters per second? Yeah, that's about 45 miles an hour running into a brick wall. That would hella suck. But cool. So we go from 20 meters per second to 0 meters per second. Our change in velocity is 20 meters per second. Cool. So our average velocity is 10 meters per second, and we're crunching in for 1 meter. You know what I mean? So we're kind of just doing those things. Like, this was actually really tricky for me, and it probably is for most people. Sometimes it's easy to go one way, but then, you know, putting in the parameters kind of in reverse, like, hey, if I only have a meter to stop, you know what I mean? So you know, finding a problem that you can actually relate to is very good. So we're going to have an average velocity of 10 meters per second, and we're going 1 meter. You know what I mean? So how long did that take? If I'm going 10 miles an hour and I'm going for 1 mile, you know what I mean? Well, that one's hard. Let's say I'm going it's probably not too hard. You know what I mean? What would be a good one? 30 miles per hour, and I went for 1 mile. You usually then you go into minutes. But anyway, I think we get it. But the other way, if you ever get tripped up on, I have a speed of 10 meters per second, and I have a distance. Because even though this is fairly intuitive and simple, you'll do this in physics where you get two parameters that you either have to multiply or divide or work together, and you don't know what. So I say the units are the equation. So we have meters over here, and then we have meters per second. And what we want is the time. You know what I mean? So we want this time. The only way to get time up top, I mean, there's a couple ways. You could just invert this, and you could say, hey, this is seconds divided by meters, and then multiply by meters. Cool, and I get meters cancels, and I get second. But I would get used to doing this. Like, hey, this is a fraction. If I divide by the fraction, the seconds pops upstairs. So I do meters divided by meters per second, and the seconds pops upstairs. So let's talk through this. Hey, I'm going 60 miles, and I'm also going 60 miles an hour. So 60 miles divided by 60 miles per hour, the hours pops upstairs, the miles cancel, and booyah. So for our problem, and we'll be done with this one, we have 1 meter divided by 10 meters per second, and so 1 divided by 10, that's 0.1 seconds. Cool. So, yeah, or not cool. I don't know if we're going to survive. I think we'll pull 20 Gs. I think that's the case. I can see it now. Cool. But crunching in for 1 meter of a car, your car crunches in 3 feet. You know what I mean? And you do all that, airbags pop. Your change in velocity is still just 0.1 seconds. Okay, so what's our acceleration? Acceleration is change in velocity, change in time. So we have 0.1 seconds downstairs, and our change in velocity is 20 meters per second to 0. So hell yeah. So we're going to have 20 divided by 0.1, and that's the same thing as 20 times 10. You know what I mean? So it's 200. So we're going to experience an acceleration of 200. Now, it's not 200 Gs. It's just 200 meters per second, but how they relate it is like, hey, 1 G is 10 meters per second. So what's the multiple? You know what I mean? And sometimes it's hard to even do this. If I say 10 times what is equal to 200? Well, we're going to have a 20 time multiple. So we're going to pull 20 G's. So in that scenario, we're going to pull 20 G's. So now I'm just really fascinated to go onto Google and say, for a car wreck, what's the most G-forces you can sustain, what the human body can sustain? What's the peak G-force that you can sustain? And yeah, that'd be fascinating. But the G-forces usually kills you if you sustain it for longer, like fighter pilots. They can sustain 9 to 10, maybe 9, but they say on Google just for a few seconds. All right, hell yeah. All right, hell yeah. So I took a little break, and this is cool because I got some more thoughts. You know what I mean? And I don't think going over this is just all for naught. You know what I mean? So this was the scenario. Yeah. So let's do some scenarios that are more like our problem, because we just did one where we had a mass, and then we have this, and the force of gravity is the driver. No force of gravity on that. But let's get it to be something. So now we're going to have a surface here, and then another surface here, and then we're going to have this mass. And so what we're going to have is this scenario, a pulley, and then we're going to have another pulley, and then another pulley. So here's our pulleys. And so in this scenario, we have the force of gravity down, and now you can see, hell yeah, the force of gravity is only operating on like mass A. This is mass B, and then this is mass C. Cool, and then you can just put them in a line again. You know what I mean? So 1 mass, 2 mass, 3 mass. Hey, this is mass A, and then you can see we do have a force of gravity on that. You can treat these as strings. It doesn't matter. You could treat them as a rigid body. But we have the other masses. So if we say F equals ma, we're analyzing this whole mass. And the only force on it is going to be the force of gravity. And now you can just visually see it's going to be, acceleration is going to be less than free fall. To get this thing into free fall, you would have to have mc, because the force of gravity is mg. So you'd have to have mcg, mbg, and then mag. You know what I mean? So the Newton, the forces on this would have to be, you know what I mean? Hey, if these are all 1 kilogram, you would have to have 10 newtons here, 10 newtons there, and 10 newtons there driving. But we don't have those two. We just have a 10 newton force on 3 kilograms. So, and again, I think what's going to be very helpful is to rearrange this equation right away. And so, or just do it just in time. But acceleration is that net force divided by, and you can just write net force, obviously. But we have that driving force on 3. So we have this, and then so we have the driving force of mag, and then divided by the total masses. That's going to be ma plus mb plus mc. And if all these masses are 1 kilogram, we're going to have 1 divided by 3 g. So our acceleration is 3.3 in this scenario. And how is this scenario? Hopefully I spelled it out for you. But like rotational stuff can be kind of tricky, but it doesn't have to be. The easiest way to make problems simpler, if you have a disc, turn a disc into a hoop, and then put all the mass right on the perimeter. And then even there, turn a hoop into where the mass is just there and there. So maybe you have like a frame, a massless frame, but then your masses are just top and bottom. So that's what we did. We put the mass here, and we put the mass there, and then we just put them on slopes like this. And the other thing with wheels is that you have a continuity. You know what I mean? So this rope, even though it goes over this wheel, the speed of this. So if this finally, after 1 second, because of acceleration, changes its velocity in that 1 second, it's going to have this new velocity, probably t1, you know what I mean? And so this rope right here will have that velocity. Well, this rope isn't slipping around this wheel, so every point on this wheel will have that velocity. So this will have a tangential velocity, and this will have a tangential velocity that way. And so we can call this A, we can call this point B, and this point C. So there you go. So it's the same thing here, is that you have like in our case, you know what I mean, this whole system initially was not moving. 1 second later, hell yeah, we have some velocity, and that's the thing. Even to do that step, I'm just surprised. Like we said that the acceleration was 1.3 g, but we didn't spell it out. Might as well just, you know, run this system for a second. That's all you got to do is just like, okay, the velocity is 0. After 1 second, we're going to have a change in velocity of this of 1/3 g. That's 1/3 times 10. That's going to be 3.3. So we have this whole velocity is going to be 3.3 meters per second. And it's going to be 3.3 repeat. Okay, sweet. So we simplified that, and now the same thing here. And again, like we're totally just saying that these are we're not doing the more complicated problem, but we're about ready to get into that, and I think we should get into that right now. So even right here, we're going to say, hey, this chunk is massless, this chunk is massless. And this thing that's like a disc that has mass, well, forget it. Let's make it a hoop. And then even farther, no, let's just make it 2 points. So this scenario is like, hey, the only 2 points on here are right there and right there. And we only want to run this system for like a half a second, you know, 1 second. And let's say this thing is so large that after 1 second, this mass moves from there to here, and it almost basically moves in a straight line. You know what I mean? It's not, you can't even say that it's like curved. You know what I mean? So we're totally throwing out all the curved nature of the problem and just trying to make it as simple as possible. And the cool thing, you know, not for the problem that given, but for our problem that we made up by supporting this whole system on an axle, we found at least an answer. You know what I mean? If we found an answer from like our easier method, you know, it's in the ballpark. It's within a factor of at least, you know, 10 or something. You know what I mean? Maybe it's in a factor of, you know what I mean? So yeah, we're in the ballpark of actually getting an answer. So it said find the acceleration of weight after the system is set free. But what you should totally know from this scenario, the whole process is like, hey, we identified that the only thing, well, no, back to this scenario where this is supported by the axle, and then you get rid of the weight. This thing isn't moving. You know what I mean? We're not going to do the actual problem yet. But from that scenario, this is your only driving force, and again, that force isn't just on this mass, it's pulling along the whole system of mass. You know, it's moving mass, and so, and if that mass is on the perimeter, you know, it's moving the same speed. But now we actually have to do a problem where, let's say, so let's go back to this drawing, and let's say these two masses weren't at like the outside. You know what I mean? They weren't in those positions. They were at halfway points. So if here's the total radius, these, like a total radius r, these are going to be r divided by 2. Okay, so now how does that change the problem? Because now what we're going to say is, and I think we just have to kind of do this conceptually. So, you know what I mean? Hey, this mass and this mass are a little bit closer. They weren't in their normal positions of like that. But what we do have is continuity, or we have this idea that when this mass A changes its velocity in 1 second, these masses, this will go this way. So we're going to have, so after you know, systems has 0 velocity, but after 1 second, we're going to have an acceleration. And so, and all it says is what's the acceleration of the weight A. Cool. So let's say weight A, let's say we have a scenario where weight A does change in velocity. And, you know, we can even throw a number on. It's got to be less than 10, right? You know what I mean? We're at least in that, and that I wanted to pull up again. If this weight is in free fall, go back to that original scenario, acceleration is 10 meters per second But the fact that it's dragging all the other weight, you know what I mean, and the only driving force is gravity on this, for this, axled spindle, if we do the simpler problem, then the acceleration of A has to be less. You know what I mean? So let's say the acceleration of A is only, after 1 second, is just 2 meters per second. You know what I mean? Okay, fair enough. But guess what? We're going to have a scenario where mass B and then mass C, mass C and mass B, their velocities are going to be twice this. So this is going to go 4 meters per second, and this is going to be 4 meters per second. So, you know what I mean? You could have a system that does that. You know what I mean? Hey, I'm going to pull down, you know what I mean? And then you know, something's going to go faster. Yeah, I think, let's even do a scenario. I think I can even do a scenario right here. Here's mass A, and mass A is connected to a couple pulleys, there and there. And this is mass B, and then this is mass C. So if this is the scenario, this is so cool just to be able to come, and this is why probably a lot of rotational problems, you know what I mean, you learn about pulleys as a foundation. And so yeah, if this has zero velocity at time 0, but then all of a sudden this gets pulled down to here, or I mean, not necessarily pulled down a distance. We kind of know that, yeah, if something's in free fall, it moves 5 meters. You know what I mean? Hey, then that is a quantity, but you know it's 10 meters per second. And we're more interested in what's the velocity after time 2. So after right here, we're going to say this is 2 meters per second. And that is going to be its velocity. Well, let's actually find its distance, though. Okay, so we're going to say that after 1 second, it went from 0 to 2. So let's play that game again. What was the average velocity? Average velocity is 1 meter per second. And we did it for 1 second. So we went 1 meter. So cool. So this distance right here and here is just 1 meter. Okay, so now let's do it. So if I pulled this... oh, this isn't going to work. My bad. Bummer. Oh, yeah. Let me think about a scenario that would actually work. All right, hell yeah. So we're back. And, yeah. So here's the scenario. So if we have this, velocity is 0, and then at some time we have, let's say, 2 meters per second. Average velocity is 1 meter per second, and so and then for in 1 second, we're going to say in 1 second we changed our velocity by that, and so our average velocity is 1 meter per second for 1 second. We traveled a distance of 1 meter. So this thing is now going to be down here, and we're going to say that distance is 1 meter. Cool. So now these pulleys get pulled down 1 meter, and so we're going to have this is going to come down to here, and then so this rope will stretch out here, but then this one will stretch out there. So that means that this pulley in 1 second will go 2 meters, you know what I mean? And so, and how do you work backwards? This mass had 0 velocity, and then all of a sudden, after 1 second, it went 2 meters. So it had to have an average velocity of 2 meters per second. But we know it started with 0 velocity, so then you have to kind of work backward. Well, what's the max velocity, or what's the velocity of this after 1 second? Well, that velocity max must be 4 meters per second. And now let's work forward. If this is going 4 meters per second and started out at 0, what's its average velocity? 2 meters per second. And this all happened after 1 second. That's why just running a scenario for 1 second is plenty. Alright, so then, so hell yeah. So now we see that the velocity is 4 meters per second, and the velocity of A is 2 meters per second. So sweet. And the same thing happens here. This velocity will be 4 meters per second. Now, the acceleration of A in this scenario is still a change in velocity of 2 meters per second in 1 second. So we have 2 meters per second squared. Yep. Now, yeah, because I was wondering how I would actually... Yeah, so we have to work backwards on this though, because let's say, like, because we have continuity. We can't just say this problem exists for a bunch of different scenarios. So holy hell, you know, we still have to say, hey, the only driving force is gravity. So we're gonna say force of gravity is on this. So let's pick an example that's just obviously not going to work. I don't think it will work. We're going to say this is 1 kilogram, this is 1 kilogram, and this is 1 kilogram. I guarantee that our acceleration will not be 2. You know what I mean? So let's figure it out. So we're going to say, now this scenario, our only driving force is and in this scenario, if we did it in a line, you can't really do it in a line. You can't say you have mass A over here, and it's pulling along mass B, and it's pulling along mass C. Like, you can't do that. You have to do it more visually in a line that says, sure, we do have mass A here, we do have mass B here, and we do have mass C here. But when we put the driving force on mass A, it's the only thing that can have a driving force of mg, which is mass of A times g. And in this scenario, it's just 10. So we have 10 newtons driving this. But it's not, if we do F equals ma, these things are not rigidly attached, and we don't have continuity in that form. So we can't just say the total mass is 3 kilograms, and we have a force of 10 newtons, therefore 10 divided by 3 is 3.3, and that would be our acceleration. And I've actually never done this one in this, you know what I mean, all this stuff I'm just kind of learning on the fly, but we do a pretty good job of it. So let me take 2 seconds. Alright, hell yeah, it's just magical. I literally turned the camera off for a couple seconds. So, yeah, this side of the equation is kind of cumulative. That's why I went back to the same scenario of like, hey, let's drop this off and then connect it to, you know, and let's say force of gravity only works on this 1 kilogram, but not on that side. And then we want to know what and let's try to use F equals ma. So, you know what I mean? We're going to say, in this scenario, they are attached. Oh, so yeah, we need a bizarre scenario. I don't even know how to come up with a scenario like this. This obviously is a good one, but I just don't have a scenario where we have check on reality. Because what we want to show is that, you know, hey, we have a force of gravity on this 1 kilogram, and it could go 5 meters. And this one could just stay put. But let's say, and then we could have the case where like they're just connected, and then I guess we turn gravity off on that side. So now we just have the 10 newtons, but on a 2 kilogram force. So let's do that. So we got 10 newtons on a 2 kilogram. Acceleration was 10 divided by 5. Acceleration is 5 meters per second. So that'll be half of gravity. Cool. But now we need this other scenario. So actually, let me turn the camera off again. Oh yeah, this is so cool. So in this case, this one is going 10 meters per second, and this one is going 0. But what we want is where, hey, velocity A, well, let's do it in reverse. So we're going to say velocity B is 2 times velocity A. So we're going to say, even though it's kind of reversed to this, we're going to say that this side is moving faster, but this side is still moving. You know what I mean? So how would we match that? And we're still saying the only driving force is just for this scenario, the only driving force is 5 newtons. You know what I mean? No, 10 newtons. 10 newtons. We have 1 kilogram, and then we have gravity just on one side. And this is a kilogram. This is a kilogram. And so let's see if I could even do this. You know what I mean? We have a force is equal to mass times acceleration, and we're going to say, hey, one of the masses is 1 kilogram, and we're going to say its velocity is what's the slower one? We're just going to say that's velocity A. But then we're going to add it to the other one, which is 1 kilogram, and we're going to say, hey, that's 2 times velocity A. Okay, sweet. So now we have a scenario where we have 1 kilogram times velocity A plus 2 velocity A, which is 1 kilogram times 3 velocity A. You know what I mean? And even this is, at this point, it's kind of nonsensical, but we know from continuity, you know, that that's kind of what we're going to have. And, oh, I'm even kind of writing this wrong, but, like, obviously we're saying force is equal to mass times acceleration, and acceleration is change in velocity, change in time, but we're saying we're just running it for 1 second. So this gets into, I think it's too heady to get into right away, you know what I mean? Or it's really good for me to go over this idea of impulse, because if I'm just saying, you know, the force of gravity is going to turn on for a second and then shut off, you know what I mean? Hey, then whatever happened after that that second to get mass up to a velocity, then they're just going to stay there. You know what I mean? Because then we can kind of analyze how fast they're going. And that is the definition of an impulse. It's just like, what does a pitcher do to a fastball? He takes the ball and then throws it. And it goes like 100 miles an hour, but then it just stays going 100 miles an hour. So that's the case where it's just like, hey, maybe gravity got turned on, it goes up to 100 miles an hour, and then gravity shut off. You know what I mean? So, and that's what we're trying to do for any problem, and just say, hey, let's just turn on the forces for 1 second, and then turn them all off. So heck yeah. So what does that look like? F equals ma is also written as F times change in velocity, change in time. I would write it like this. I think writing it as dv dt gets a little scary, because like this is literally, we're changing the velocity 1 second. So we have F is equal to mass, change in velocity, change in time. And now we're just saying, hey, let's say this is just 1, and we're just going to, you know what I mean? If this time is just 1, and my acceleration is in meters per second, cool. We can kind of write an equation that's just F equals m, you know, just change in velocity. Now this is the force required to change the velocity for 1 second. And so the way to do this technically is do this. So we have force is equal to mass, change in velocity, change in time. We're just going to multiply the acceleration by change in time, and that's going to give us the change in velocity for that second. But we have to do the same thing to both sides of the equation. And the definition of a force, you know, times 1 second, or any time, is the definition of an impulse, and sometimes they use the character P to describe impulse. Okay, so, but that's why I can still kind of do this. I can say, hey, force is equal to that mass, and then just the velocity is after 1 second. You know what I mean? I'm basically doing the most basic thing you can do with an impulse. Like, it's just, it seems like a cheat code. But yeah, you know, you don't have to get too deep into this impulse thing. You can just say, okay, yeah, this makes sense. The velocities after 1 second will be this. This will have a velocity of, you know, yada, and this will be twice that. And if that's the case, well, then we kind of have this continuity that mass times the change in velocities kind of have to. So this scenario of one mass going, you know, let's say 1 meter per second, and this going 2 meters per second, is synonymous with just, if you just had 1 kilogram going 3 meters per second. Or you could you could say that I think the other way to say it is it's also synonymous with whatever this is. This also has to be synonymous with 2 kilograms. How's this going to work out? I feel like, let me turn off the camera. I feel like I made a mistake. Alright, no, I didn't make a mistake. It's just, maybe it's just the way I wrote the equation. I don't know. You know what I mean? For this scenario, we were trying to find, and let's get the force over here, because over here we were saying, hey, we only have a 10 Newton force. So we're going to say 10 Newton force is equal to 1 kilogram times 3 times the velocity at A. So that's going to be 10 divided by 3. So our velocity of A is going to be 3.3. Now I feel like that's 100% not right. Oh, no, that's 100% right. I don't know what the hell problem I was thinking about. Yeah, no duh. Okay, because we're doing a free fall problem where just in general, it wouldn't matter if you had 1 block or 2 blocks. If they're in free fall, their velocities are going to be 10 meters per second after a second. And then we did this scenario, well, hey, let's just say this block is moving 10 meters per second, but this isn't. And then we did this scenario that says, hey, let's say they're connected together, but force of gravity only works on one side. Well, then the velocity of both blocks is going to be 5 meters per second. But then we had this special case where we have both blocks side by side, and they're on tracks, but for whatever reason, if this block gets up to speed, this block will be twice that. You know what I mean? And then I guess it wouldn't matter. The force isn't necessarily over here on this block. It's kind of on the system. So we only have 10 newtons driving the system. So let's write it again. So we have 10 newtons driving the system of one, and then so yeah, you have 10 newtons doing this, and so you're going to have 10 newtons is driving, you know what I mean, and just the way it's written, like it doesn't show what the 2 kilogram, but it says that this says that you're just solving for one of the velocities. So the velocity at A will be 3.3. And if the velocity at A is 3.3, the velocity of B is twice that, is 6.6 meters per second. And now, is that something that that jives? Let's see. But I guess, but we were still saying, you know, for this scenario, we still only wanted to put the force on one of them. You know what I mean? So yeah, let me double check my numbers on this. No, it's bizarre. It's so funny. No errors on this. It's just, you know, okay, this scenario where we have the force just on one block, but connected to the other block, no force of gravity, it's going to go 5 meters per second. Now, this one, force is on one, but then we have like this velocity difference due to continuity. You know what I mean? And it wouldn't matter. You know, we could have just said, hey, one of the blocks is stationary, the other block moves, and then, yeah, one of them would have gone 10 meters per second, the other gone 0. But then the average between them as a system is going 5 meters per second. And so that's what we have here. This block goes twice the speed at 6.6, but that plus 3.33 is 10, and then we divide by 2, and we get the average velocity of 5. Which would we expect? That's the whole take-home message. I guess that I'm just kind of spelling out in you know what I mean, in just bite-sized chunks, that if I have a force, you know, some sort of driving force, and then we're pulling other masses, and sometimes those masses are moving at different speeds, or even twice speeds. And then some of those masses aren't moving, you know, at all. You know what I mean? Hey, they don't. But yeah. Yeah, the masses that aren't moving at all, hey, it's like you're pulling a chain off a table, but then some of the mass isn't moving. Well, yeah, if this is the mass that's moving, well, hell yeah. Then you're actually, that driving force is only operating on those chunks of mass. And if you have a velocity difference, Because yeah, I love the chain fountain. That's such a cool one, because you are going to have continuity through the system, but then you're always going to have these speed ups and slow downs too. And you have to have a velocity gradient, because hey, when you pull on a chain, the end of the chain's not moving until this kind of snake reaches it, and then it slowly starts to move, and then it jerks and then stops, jerks and stops, and then finally gets up to that free-flowing, speed. So yeah, so it's just fascinating. But what we're showing is that you just can't, and I don't know, I'm telling you this just because like it just seems, this would have been bizarre to me that, okay, so I have a driving force on a mass, but why if it drags all the other mass behind, why is it gonna not change? You know what I mean? If F equals ma, you know what I mean? And it looks like I have a force on a mass. Why isn't that accelerating? Well, it's because that force is operating that mass, but due to continuity, it's pulling all that other mass with it. And so, and rotation is just an interesting one, because that's where you want to put the masses out at the edge, because now you can just turn them into tangential velocities. And it's no different than if they were just resting on tables and then moving that way and that way. But you can see that if you have a disk, you know what I mean, hey, the tangential velocity here is only half of what the tangential velocity at the edge is, you know what I mean? And so, and the tangential velocity here, due to any sort of spin, you know what I mean, if I have a rope on this, and then I'm spinning this, well, sure, like if this moves 1 meter, heck yeah, this moves 1 meter, and you can say the velocity of that chunk of mass is going to be that. And you could say, hey, this velocity of this chunk of mass is also moving in that same line. And then so that's, yeah, let's do that just real fast. Is if you have a hoop, you know what I mean, and I have this driving force A. So we're at least back to, we can visualize this and we can just do it a lot faster now. But then all the chunks of mass are on the outside edge. Cool. So this whole scenario, I just do linear. I just play it out like this as a chain on a frictionless surface. You know what I mean? And now I say, hey, there's a force over here, which is just gravity, mass of A times G. You know what I mean? Mass of A times 10. And if this is 1 kilogram, that's 1 times 10. Shoot, we got 10 newtons on this. And now we're going to say, hey, let's say we have 10 of these, but this whole thing is 1 kilogram. So now we have 1/10 kilogram, on all of them. And so continuity would say we have F equals ma. We have a driving force of 10 newtons. The whole system weighs 2 kilograms. You know what I mean? 1 kilogram here, and then 1 kilogram there. So we got 2 kilograms. The acceleration is 5. Cool. So and that's what's going to happen with rotation. Whatever your driving force is, you could throw it off a cliff. It would go 10 meters per second every second. Increase in velocity. But because it's like spinning all this other mass, hell yeah. And then you could just say, you know what I mean? I think it would be very useful to do both scenarios where, and again, this is still on a spindle. We're still doing the easier one. We're about ready to get into the toilet paper roll, holding onto a toilet paper roll and then having it roll. But heck yeah, so let's say we have this scenario. Let's say we have a spindle, and we do have this driving force ma, and for whatever reason, we're able to spin this spindle. You know what I mean? So when this, You can just imagine, like, hey, maybe this rope is kind of wound around this spindle. So this spindle will move. But then we're saying, hey, this spindle is really long, you know what I mean? And it's still supported, and it does have mass, but it's just, and it's like real heavy, but just real tiny diameter. Now the question is, you know what I mean? Will this fall in free fall? And the answer should be yes. You know what I mean? Don't visualize this answer as no, because we're taking this to be point masses. You know what I mean? And I know you can't even something that is visible to the naked eye is no longer a point mass. You know what I mean? If you can see something to the naked eye and you spin it, hell no. You know what I mean? It'll look like you know what I mean, at least this. Sometimes I take a disc. This is a good one. I haven't done it in this video yet. But you take a disc, and that can just be whatever the mass of the disc was, 1 kilogram. You do this. This is a quarter, this is a quarter, and this is a half a kilogram. And so, and then you throw it on a rigid body. You know what I mean? So if we're spinning this is the same scenario. And this, even though we draw it like this, can just be drawn as point masses. You know what I mean? So you could still say this. This is 1/2 kilogram, this is 1/4, this is 1/4. But you're still spinning it. So if you're spinning it around this axis, yeah, you have a tangential velocity there and a tangential velocity there. But this is representative of a cylinder, because most of cylinder, hey, the mass is kind of inside where it's not like moving on the edge. And actually they're and this is a good one to do, because if you do have a cylinder, technically no mass is at the edge. You know what I mean? Like all of it's inside, you know what I mean, the cylinder. So that's where a hoop is a special case, where a hoop has to be pretty thin, but then, you know what I mean? Hey, you could just say it's all at the edge. You know what I mean? So that's the cool thing about a hoop. But with a disc, hell no. Like the majority of it's not moving. Like it's moving hella slow in the middle. You know what I mean? So that's kind of the difference there. So in this scenario, hell no. This is going to accelerate at g, 10 meters per second squared. All right, nice. All right, hell yeah. So let's do it. So now I think we are ready to tackle the actual problem at hand. So now what we're gonna do is we're gonna just get rid of this mass right here, and then we're gonna see that this is literally like a toilet paper roll of toilet paper. That's unspooling itself. So if here's the axis, you know what I mean, hell yeah, this is going to fall. You know, we have a force of gravity, let's say. And so how do we simplify it just from all that stuff that we just learned? Like what can we do to this just to make it simpler? So I'm going to say, hey, a disc. You know what I mean? Well, didn't we say you know, we can just make it like 3 masses or something? Well, let's even simplify it more and just say this isn't a disc, it's a hoop. You know what I mean? And then instead of a hoop, we're gonna say, hey, like the masses are just on the outsides. And with a hoop, it's kind of cool. Well, never mind about that. But I haven't proved it. But yeah, I was doing one problem with the hoop, and if you throw all the masses at the corners, man, and just say if this is a 1 kilogram hoop, and you say these are quarter kilograms each, man, you can just do so many cool problems, you know, just doing that. So we're kind of doing the same thing here. We're going to say we have a half a kilogram. Because for our problem, just mentally, we're going to say this is 1 kilogram and this is 1 kilogram. Cool. So yeah, so our new problem is yeah. So we're looking at a 2D view. We have this hoop with a mass right there, and then a mass right there. And yeah, these are rigidly fixed. And let's see. And now this is connected. Just at the very instant, we're taking this problem and making it look like this. You know what I mean? So that's what's gonna happen. That's what we're gonna show. Like this molecule ain't moving, but then this whole cylinder rotates or falls. You know what I mean? This way, and so. what we're going to show is that, oh man, yeah. So cool. I don't know if I'm making mistakes on this, but obviously, if we in our scenario, sure, we have force of gravity on this, but then we're gonna have an equal tension up. You know what I mean? That's what I'm gonna say for that one. Even though for the system, this tension up, oh bummer. Yeah. Well, we're not even going to we're not going to turn this into just a tension up on this. We could do that. Yeah, no duh. Holy Toledos. You could have a string attached to a chunk of mass, and then over here a lightweight rod attached to another chunk of mass. And then we're just saying, hey, this gravity, which is mg, which is going to be 1/2 kilogram times 10, so it's going to be 5 newtons. We have a tension of 5 newtons there. You know what I mean? So obviously, that's why I don't want to get into numbers. We really don't need to do that. So what we're showing is that, hell yeah, we got a force of gravity on this one. It's going to be 1/2 kilogram times 10. That's going to be 5 newtons. And and now this mass is going to move. So after 1 second, you know what I mean, we're just going to say it, and we're going to say hell, like this radius is so big that after 1 second, like it moves to there, and that's going to be 5 meters. You know what I mean? So, and I think that is a good thing to do for rotational problems, where you're just like, cool. So like that's how far it moved, and yep. Yeah, and so, well, let's see. So yeah, so we turned this thing into just 2 masses on a hoop, and then basically almost on a pivot. We were just saying, hey, this is just a pivot right here, and then the mass is over there, and it just pivots down. And it's not too far off, because let's say I had a circle on a ramp, and I haven't done this problem a whole lot. I'm kind of new to this rotational stuff. That's why it's kind of interesting watching my videos, because you're just like, well, if I can get it, you know what I mean, maybe I can stumble across some things that, you know what I mean, because I just refuse to use the equations that you're actually using in the end. You know, I don't mind looking at those and then doing it that way, but I still am a little bit slow on the comprehension of, you know what I mean, that torque causes I alpha, and yeah. So anyway, stuff like that. So if I have a disc, you know, on a slope, I can do that 2 mass in the middle, 1 mass at the ends, and so now, and then it's going to roll without slipping, which is the same thing here. It rolls without slipping. I'm going to take this ramp and just make it hella. And so it's basically vertical. And then so I'm going to take my thing, and I'm just going to make it 2 masses, 1 mass. And so now, and this is going to be on a stick. And so so here, this is what's actually going to happen. So when we start to solve the problem, we could solve it, you know, in this way, where now we have that same scenario. We have the force of gravity acting on both of these. This is a pivot, so, you know what I mean, it's kind of like the force of gravity doesn't count. So I like that analogy. And this is going to be 1/2 kilogram. This is going to be 1/4 kilogram. And so we're going to have 5 newtons on this one, and then 2.5 newtons on that one. We use F equals ma. And now we do have a continuity where these things, you know what I mean, after time 1 second might be down here. And this is cool, because I can even, yeah, I'm just doing this all on the fly, but I get it. We changed some sort of angle, and so you know what I mean, hey, we have 0 radians per second as our angular velocity. And then let's say we do have like a 30-degree angle. Let's say we have 0.5 radians per second. So if this is the case, it's the same thing with velocity. Hey, we're going 0 meters per second, and now we're going 0.5 meters per second. No. I apologize. That's absolutely the opposite. In 1 second, we went 30 degrees, which is 0.5 radians. So it's like saying in 1 second we went 0.5 meters. How fast did we do that? Well, we do our average velocity is 0.5 meters per second. And then we went from 0 to our max, which is, our max has to be 1 meter per second. And then you can work the other way. If I had a change in velocity from 0 to 1, average speed is 0.5. And I did that for 1 second, I went a distance of 0.5. So the same thing with angles is the same. And I think I just need to do it more, and most people do. I think the second you start using angular velocity is like there's this idea that you're already at like a smarts, that we can just say things that you should know, but no one does. And then so it just hella gets lost, and then everyone just graduates and says, I'm never going to do those problems again. Yeah, so hell yeah. So in 1 second, yeah, these are going to move down, you know what I mean? But continuity says they have to be in the same line. And we're going to spell that out with an angle of 0.5 radians. And so we went from we had an angle of 0 radians here, angle of 0.5 radians. So, and so it looks like we went 0.5 radians per second. This is our average angular speed. But the angular speed here is 0 radians per second. And so I must have a max right here. My actual angular velocity right here must be 1 radian per second. And now we can work backwards. 0 angular velocity here, 1 radian per second here for my angular velocity. Average has to be 0.5 radians per second, and I did that for 1 second. I must have moved an angle of 0.5 radians, which is 30 degrees. And just to spell it out even more, here's a circle divvied up into 6 chunks. It's 360 degrees. 360 divided by 6. You know, and I don't even do that one enough. Yeah, 6 times 6 is 36. So therefore, 6 segments of 60 degrees is 360, and then you have this, and what a radian is, it is a good one to do. So you have this radius. If I measured this string and then draped it around the circle, I'd get to about there. And it's just a cool property of circles. And it has nothing to do, it has most everything to do that, and it's bizarre. I think now I'm going to teach this way. Every time I talk about radians, well, let's talk about diameter. Because basically, there's the diameter. What the hell's the circumference? Circumference needs its own little cool symbol. Because the C doesn't do justice. No one uses circumference. But circumference is just 3 times d. Don't use pi. It's just 3d. Bible says 3. And hell yeah, that was a pretty good joke. And so anyway, so we have I'm getting, anyway, but yeah, it's a pretty good one. All right, so we have so there's 3 diameters. So if you measure this diameter with a string and then draped it around the circle, well, you would only get a third of the way. So we would have to like kind of divvy up a circle to look like that. You would get to there, you would get to there, and so I'm the first to spell that out. So I'm going to spell that out pretty much every time. But it's just a weird property of or maybe it's not. No, it kind of is. But anyway, yeah, radians are just useful because if you ever do sine of 0.5 in radians, that's actually 0.5. If you did it in diameters, if you said you went a half a diameter, well, that would be 60 degrees. So what's sine of 60? Well, that's going to be 0.866. And so if you said you went sine of 1 diameter, you're going to go 0.866. And, or does it still work? Well, let's say you went sine of 0.5 diameters. You know what I mean? And so, oh, yeah, no, duh. No. So I apologize. This was 0.5. So 0.5. If I went sine of 0.25 diameters, so if So again, 60 degrees is a radian. Half of a radian is 30 degrees. But and then so here's the radius, and then I drape that string, I get to there. If I got halfway, I'd just get to there 30 degrees. But if I had a diameter, holy hell, I actually moved twice all this. So if I had a quarter of a diameter, I would get to 30 degrees. So sine of 0.25 diameters, and let's write this out, sine of 0.25 diameters is equal to 30 degrees, you know, basically. Oh, no. You don't get degrees when you do sine. So sine of 0.25 is going to be 0.5. You know what I mean? So that's what I was spelling out. So it's only kind of this magical, cool deal. And maybe it's not super magical and I just don't see the obvious. But yeah, if you do sine of 0.5, you get 0.5. But if we talked in diameters per second, which could be a normal thing to talk about since we talk about radians per second, which is just the radius as an arc length spelled out, and that's going to be your angle. We could also say the diameter spelled out is also an angle. You know what I mean? And so there's about 6 radians in a circle. So if you were going 6 radians per second, you're doing about 1 revolution a second. Cool, but there's 2 pi. There's 6.28. All right, that was a good little tangent on that. But now we have to go back to this one. Okay, so because this is that continuity thing, you know what I mean? And let's just get a bigger picture. So we have this mass, and we have this bigger mass too, and then we have this mass. And so we have a force of gravity on this of 5 newtons, and then is that right? Yeah, and a force of gravity on this of 2.5 newtons. Due to continuity, they get to the same location. But now look at this. We know. And we're just going to say they went 30 degrees, and so we already just solved that. The angular speed at this after 1 second is 1 radian per second. Cool. So now we want to know what the tangential velocities are. And so we're just going to say this whole distance is, do we want to say it's 1? Yeah, I think we want to say it's just this whole distance is 1 meter, so this is 0.5 meters. And so the tangential velocity of this guy is going to be, how do you find tangential velocity? Well, no one knows about radians, so I like to say that, hey, if we got radians per second, radians times radius is something normal. So if we multiply by the radius, we get tangential velocity. So let's do that. So we have 1 radian per second times 1. So this velocity is going to be 1 meter per second. Now this one is going to be 1 radian per second times the radius of 0.5. Oh, so its velocity is only going to be 0.5 meters per second. And man, I'm really proud of myself on this video because, you know, I mean, no one's going to spell it out so hardcore, but we just did this problem. Remember? We had one mass moving twice as fast as the other. The only thing in this scenario is that this is a half a kilogram and this is a quarter kilogram. But let's set up our F equals ma. So we're going to say, hey, F equals ma. We have, and we're going to say the total driving force in this kind of direction is going to be 5 newtons plus 2.5. So let's see if I'm doing this right. So we have 7.5 newtons, which makes sense because it's like gravity got turned off for that one. So in this direction, yeah, that's what we've got. And then we're going to do that same scenario where we have this 1/2 kilogram going a change in velocity of yeah. You know, we actually can't say what these forces are. For this, we already chose our continuity that we went 30 degrees, you know what I mean, with these masses. So actually we can't specify the force on them. We already made the distance. So we actually just have to say this is F and this is 2F. So I'm going to say that this point is A, B, C. So this is FC, and this is FB. So we can say that FB is 2 times FC. Cool. So we actually just don't know what the forces are. We can't just make up a problem and then make up how far it went. That would be like saying, hey, I jumped off a cliff and after 1 second I went 20 meters. Well, no you didn't, unless you had a rocket pack on you, and that would be the extra force. So if you want, you know what I mean. And so here you wouldn't know not the force of gravity, just the force in that direction to cause that distance. So we just did this because we're just like wanted to show that, hey, if this plays out at an angle of 30, both these are going to be along that line. And then that 30 degrees is just a really good one because, hey, you went 0.5 radians, and that must mean that your velocity right there is 1 radian per second. So I think this is a really good way to do that. And I'm not well versed, you know, this is kind of the first time doing these problems. So once we go forward and find that force, then we'll actually go backward. You know what I mean? Because if this force over here says it's like, you know what I mean, 15 newtons, well then we know that we didn't go 30 degrees. It's probably a linear relation, or maybe it's, I don't know if it's a linear relationship. Maybe it's a squared relationship or something. But we didn't go 30, we went less. You know what I mean? Because it would take a driving force of 15 newtons to go 30 degrees. You know, that might be what we come up with. All right, so let's try to do this continuity because it is fascinating to me. We don't know the forces, but we do know that we have a force on this one of Fc. FC, and then we know that this is 2Fc. So sweet. So we have a force over here, this part of the equation, so we have a force of 3Fc, and then that's going to equal to the masses that we're analyzing, so that's going to be 0.75 kilograms. No, we don't want to do that. No, we got to break it up. Because now we're going to do that scenario where we're basically doing that impulse. Where we're saying force is equal to mass times change in velocity, change in time. But we're really going to say, hey, let's say this is 1. And again, if we say this is 1, you kind of multiply by change in time of 1 here. And so force times 1 second is what we call impulse. So we have this, impulse of linear momentum. Impulse is mass times change in velocity. So if we have a force times time, that's mass times change in velocity. I just don't like to write equations like that because even this is too much for my brain to handle. And it's just nice to do them in a way where it's like, hey, we're just using F equals ma. And we're just saying, hey, we have a force on a mass and it's changing its velocity. All right, so hell yeah. So I'm kind of excited about this one. Grab some extra sheets of paper. And so what do we have? So we have this 3, I guess we don't need too much extra. So we have this 3Fg, but now we have to go to, and we're saying this one's going 0.5 meters per second and this one's going 0.1. So cool, let's do it. So we have that mass times change in velocity, and for the 1 second. We're only analyzing after 1 second. We got that part. It's pulse. And so we have this ½ kilogram times 0.5 meters per second. That's our change in velocity on the ½ kilogram. Plus, this is going to be a ¼ kilogram, 0.25 kilograms, but we're going 1 meter per second. So cool. Well, what does this all add up to? 0.5 times 0.5, that's 0.25. And this adds up to 0.25 times 1. Okay, 0.25. So this is going to be equal to 0.5. Like, who cares what the units are? They're units of newtons. Yeah, they're units of kilograms, meters per second. I'm glad I focused on the units because we got kilogram and then meters per second. That's the units of Newton. Okay, hell yeah. So now we can just solve for that force. The force required to do that scenario that we just showed will have to be, force of C is 0.5 divided by 3. So that's going to be 0.5 divided by 3, and it's 1.6 newtons. You know what I mean? And this should make sense of why it's so low, because we say if you have a mass and it's under the influence of gravity, after 1 second, it's going to go 5 meters. You know what I mean? So, and now we did this scenario where, hey, we had a mass on a string that's 1 meter, and then we're going to drop it. Look, under the influence of gravity, this thing wants to go 5 meters down here, and you're just going to say it swings 30 degrees? You know what I mean? Well, hell no, it's going to go 5 meters. You know what I mean? And this is where, like, obviously, if this mass gets to down here and is just stationary, you know, it'll just stay at rest because, you know what I mean, there is no driving force. Like this force is driving tangentially here, but then once you get down to here, this force isn't, and then here's the direction of the path. Hey, only a component of this force is in that direction. You know what I mean? Most of it's kind of just not in the direction. So only a little bit. And then once you get the hell down here, hey, this is the force of gravity. None of force of gravity is in the direction of motion. So, but we're still trying to just simplify problems of just like the instantaneous thing that happens. But this sucks. It is the suckiest thing because you can't use a change in time of like 1 second. The only way you would be able to do that, you could do this problem in reverse. Is just like, hey, if I did play out 30 degrees and I want to use the force in gravity, hey, how long does this thing need to be? And I might want to do that one actually. Yeah, let's let's do that one, because anytime you get an equation, you can just kind of see what you're doing. So we have 3 times the force Fc, and we're going to say, hey, this is going to be whatever Fc was. If it was gravity, this was going to be that quarter kilogram. And if we do have gravity on it, it's going to be 1/4 times 10. That's going to be 2.5. And then we have 2.5, and then we got 5 on the other one. So it's 3 times 2.5. Yeah, that's that 7.5. And that's what we wanted to do. We want to do F equals ma. And so we have 7.5 newtons. And then what we want is like, hell yeah. And we're just going to run it for that 1 second. Cool. So we have this scenario playing out where... but we just don't know this distance right here, or this distance. So we're gonna say, well, we're just gonna say the whole thing is L, and this is L divided by 2, and then we'll solve for L. Hell yeah! So 1.75 newtons is equal to hey, let's do this mass. That is 0.5 kilograms, and then what's its velocity? You know what I mean? Hey, we're still doing this scenario. Nothing's changed here. The radians is 1 radian per second. You know what I mean? We set up that as our continuity. Or I mean, just as we just wanted to set that up as our problem statement, but we have to vary this length. Okay, so oh, this is cool. All right, so yeah, so what's the velocity of this? It's omega times the radius, and so we have 1 radian per second times the radius, which is L divided by 2. And now we come over here to this mass. We have 0.25 kilograms, and then the same thing, 1 radian per second. And then this is going to be omega r, so it's just the total length. And hell yeah, now we just solve for L. Cool. So this is going to be 0.5 divided by 2. Isn't that 0.25? So we have 0.25 L, 0.5 divided by 2. And then over here we got 0.25 L. Cool. So we got 0.5 L is equal to 7.5 newtons, and it feels pretty good. So we have 7.5, and then we got to divide by 0.5. And so we get 15 newtons. No, we get 15, sorry, I don't even know what the hell I'm solving. But so right here, the units on this were kilograms per... Well, yeah, I don't know. You know, it's an impulse. So this was times the change in time of 1 second, but we're not doing that. We're totally just doing it by like what do you call it? Intuition, you know what I mean? We're saying we ran the force for 1 second, so we're going to have a change in velocity. We're totally just spelling out what an impulse is for 1 second, but not writing the equation for impulse. Force change in time is equal to mass times change in velocity, or force time is mass change in velocity. We're just we're doing it the intuitive way. So hell yeah. So our length is 15 meters. So I'm going to use this for other problems where, you know what I mean, if I want to, so now in every problem that I have a hinge, and then whatever mass is out here, and then I want to go 30 degrees, or 0.5 radians, which is close enough to 30 degrees. Now I need to make this length 15 meters for gravity to do that. Okay, hell yeah. Alright, hell yeah. So we're back, but I'm kind of bummed out because, you know what I mean, now I'm finally reading the problem, and it says pulley B has mass B, but then it just says, hey, also known, you know what I mean, who cares, is just the moment of inertia of this whole system about this axis is just I. You know what I mean? So you don't even have to solve for it, but we're not going to do that. You know what I mean? So, and then obviously the other thing that's known as the differences in the radiuses, this one's twice. So what we're going to say is that the mass of this axis is going to be like MB, and it's just this portion, you know what I mean? And then we're going to say this is mass C, and cool, because then we have then we can actually then we can solve for the moment of inertia ourselves. So yeah. So that'll be sweet. But I'm saying that's a better route to go, because now we know that this MB, but this MB is both these masses combined. So this is 1/2 MB, and then this chunk is going to be 1/2 MB. Cool. I think we got it figured out. Now this is interesting because this mass sticks out over. So again, if we do this with you know, just a toilet paper roll, and anytime you do a disc, I don't have time to go over this again. I just assume it's going to work, and that's why I always want to use something until oh it doesn't work. But we're going to do the 2, 1, and 1. So if this is 1 kilogram, hey, this is 1/4, 1/4, and then 1/2. And this is at a pivot, and so hell yeah, we just did the same thing that we had. But that's for this mass, that's for this spindle, you know what I mean? If we look at this thing, well, and this is a radius R, so this is going to be D. So yeah, let's do a diagram of this. 1, 1, 1, 1, 1. So this inner one has that radius, and the outer one has that. Cool. So if we said this looks like that thing, so let's do an actual drawing of this. Then this is the inner spindle, and oh, because this is 2R. No. So we got it. So if this is R, hey, this outer spindle is 2R. Like, holy Toledo! I'm glad I did that, because visually, no, damn it. This is from the center. My bad. No. So yeah, it's not. This distance right here isn't just some 2. You know, it's actually R is the radius. It's not 2D or something, or 2 times the thickness. It's actually the radius from the center. Cool, got it. And so it does look like that. So here is the spindle, and then we just go, and then here's the radius of the spindle. So we just go one more on both sides. And so now this thing will have, you know, so now we're gonna superimpose these two things. So if we superimposed the bigger mass, and we're definitely gonna say, hey, let's say this mass is 1 kilogram, but then this one is 2 kilograms. Yeah, because just visually it looks heavier, or maybe not. Maybe it's all the same. But no, let's stick with just 1 kilogram, because we're going to have the same thing here, but it's just going to, oh yeah, it's going to be the same thing, but it's just going to be just a little bit bigger. So we have 1/2 of that mass, but then we have the quarters way out here. So we have a quarter kilogram. So yeah, so we're going to have, this is 1 kilogram and this is 1 kilogram. And shoot, yeah, that thing does look heavier. So 2 kilograms there and then a 1 kilogram mass to drive. All right, so but in this scenario, where's the fulcrum? See, the fulcrum is just right there. So here's your pivot point for this inner cylinder, and here's the pivot point for the outer one. And if this is the pivot point for the outer one, hey, we got gravity working over here. You know what I mean? So we got the force of gravity on this one, and it's going to be It's going to be 2.5 newtons. We have 5 newtons working on this one, and then we have 2.5 newtons working on that one. But yeah, these two don't balance. But yeah, if here's our pivot point, so now what's our net force? So our net force in well, yeah, this does kind of balance out at like you could redraw this just from a very intuitive perspective. And so we got 1, 2, 3. Holy Toledo, 1, 2, 3, and then I just kind of drew these just a little bit too big, but okay. So if we have a quarter over here, it balances with one of these quarters. So we're just going to eliminate this one and then just say, hey, this one is a quarter. So we have a quarter down here. So we got 2.5 newtons driving this way, and now we just have a quarter or 2.5 newtons driving this way. So now we actually have a visual representation of what's actually going on, because it's a little bit less. Well, I mean, it's this problem. Yeah, you would want to do this to figure out, and all we're doing is trying to figure out. Well, I don't know what we're trying to figure out. Oh no, we're not solving this from a torque perspective. We're solving it from a continuity perspective, and it's fabulous. It's really cool. We're saying, hey, we have these masses, and then we have the. So yeah, let's try it out. So this is going to be our driving forces, 2.5 and then 2.5, and now we have to, yeah, let's draw this one more time, because we have to superimpose all the masses back in. So we're going to say, hey, we got 1, 2, and then we have another radius out there. So this is the inner radius. Sorry to draw so small. Now, and then this inner radius has, we're going to say 1 kilogram. This outer radius is 1 kilogram. So we have a half right there, quarter. Now this bigger one is a half right here and a quarter out here. These two halves are going to add up to 1. So we're going to have 1 kilogram right here. And then we're going to have a quarter right here, a quarter right here, a quarter right here, and then a quarter right there. So so heck yeah. So this is what it's going to look like, and our pivot point is right there. You know what I mean? So so when this thing turns, hey, this mass is going up. And then these masses are going down. But it doesn't matter what directions the mass are going. What's important, you know what I mean? It's like, even like right here, it's just like, who cares? You basically do the system, and you say, when we have a driving force on this mass, hey, these other masses are moving. Maybe this one moves 2x, this one moves 1x. So now we have a visual representation that we can handle that. And because right here, we only have a driving force of 2.5 newtons. Cool. So and we're gonna have to do this problem kind of in two ways again if we want to put some numbers on it. All right, hell yeah! I was just thinking, I'm so pumped because you know what I mean, and you'll have to bear with, you know what I mean, the idea that a disc can be a 2 mass there and a mass and a quarter masses. So if we have 1 kilogram disc, it's the same thing as spinning half a kilogram in the middle and then 1/4 kilograms on the perimeter. But I have done a couple problems like that with like 100% success. I should do a shorter video to prove that. But I'm just gonna, like, that's my kind of cheat code. But you could also just do the same thing and turn it into a hoop where half the mass is there and half the mass is there, and then run the scenario. So you know what I mean, you would probably get fairly close answers, but this is more representative of a disk because more of the mass is in the center where it's doesn't have any tangential velocity. All right, sweet. So yeah, this is super cool. So we're super close. And I think I am going to do kind of the same thing. We're going to make this go to a 30 degrees, and then by that same scenario, that's going to be an omega right there of 1 radian per second. If we know the angular speed after 1 second, we can figure out what the tangential velocities are. And so, hey, let's use our F equals ma and see if we can just solve for this stuff, because you know all these are r, and so this one from our pivot point. See, our pivot point's not in the middle. Our pivot point's there. So if we go to this one, that's 1r, r, and then out to there, that's 3r. And then if we go that direction, that's the r the other way. So if this spins this way down, omega. Then this has a tangential velocity up. This has no velocity. This will be the pivot point. And then these have tangential velocities down. And just in general, hey, this will be the same tangential velocity down as this one's up because of the same distance from the pivot point. This will be twice what these two are, you know what I mean, magnitude-wise. And this will be 3 times what these two are. Cool. So hell yeah. So I don't know if we can just solve this in one go. But we're still going to do that same thing, mass change in velocity, change in time. Hey, 1 second, you know, it's kind of like this, change in time, but it's just 1 second. So we're trying to make up our own equation of just saying, hey, I like the idea of force and mass, and I like the idea that acceleration is change in velocity, so we can just say change in velocity. And then we can just go to town. The only driving forces on this is going to be 0.5 newtons. For this case, you know, because is that jive with reality? After all that, we were saying this is 2 kilograms. So if this whole thing was in free fall, we would have 2 kilograms times 10. That would be 20 newtons. So should we go back and figure out why this is only yeah, because I think that's a wrong statement. Yeah, because this was just for, no, I don't know. No, I think that was a wrong statement. Yeah, we have a 1 kilogram, because if we add up these, you know, I mean, we'll have a half a kilogram there, and then 1/4 kilograms right there. And then we'll have 1/4 kilograms right there and half in the middle. So we're going to have 1 kilogram in the middle. Hell yeah, force of gravity is going to be on that. I'm glad I caught that error. That would have been a sucky error. So anyway, so we're going to have, on this one, we're going to have 10 newtons. 10 newtons. And then on these guys, we're going to have 2.5, 2.5, none on that one, but then 2.5 there. So this one is going to cancel a 2.5, so I'm just going to call this 7.5. And I'm just going to say torque-wise, those are going to cancel. You know what I mean? So now we have this one's gone. We got 7.5, 2.5, 2.5. So that's 5 plus, that's 10 point, that's 12.5. So we have a driving force over here of 12.5 newtons. 12.5 newtons. And we're turning the problem into a linear problem. We know due to continuity, their velocities have to follow, you know what I mean, these sorts of rules. So we're gonna just get a generic. So we're just gonna say velocity 1. That's gonna be the velocity at 1 radius over, or just velocity just r. So just the velocity of r, and we're gonna say this is velocity r, and then this one is gonna be 2 vr, and then this one is gonna be down with 3 vr. Sorry, I'm just writing so small, but it's just really good to talk through the ideas of what's going on. And hell yeah, I think we're doing a good job on that. So with this equation, we have we don't have to analyze this one, but this one we do. Even though it's going up, it's not like it's canceling out anything. No, we have a driving force that's what we just came up with. We have a driving force of 12.5 newtons. You know, because this one doesn't count; it's on the pivot, and then we got that. But yeah, any other masses that's actually moving, you know, back to, I mean, that's the whole reason I've done this video, is just like, yeah, cool, you got a driving force like on mass A. Cool, but it's also connected to all these other masses in some sort of continuity way, and maybe some sort of weird continuity way. Because even with ours, we got this 12.5 newtons. One of the masses is going in the opposite direction, but it doesn't matter. It's still a mass in motion. You know what I mean? So, because, yeah, this one's going 2, this one's going 1 that direction, this one's going 2 that direction. But guess what? This one's going 1 that direction. So we have this chain. Hey, you pull on this one with a force, and then all these other things happen. But still, F equals ma applies. You know what I mean? It's kind of like that total. Yeah, so man, that's so hard to explain when you break it up. I definitely lose a little bit of the fundamental understanding of it, but I definitely for sure know that if you only have a certain amount of driving force, and then, you know, on a chunk of mass, it's only going to go this slow. But then if one of that chunks of mass stays put, then the other is going to go faster. You know what I mean? Because you're still, you know, F equals ma. If you have a force, you can change that mass by a change in velocity. And if it's just 1 second, the number on acceleration will be the change in velocity. And that's kind of this impulse thing that we're talking about. You just multiply by 1 second. Okay, sweet. Let's solve this. Okay, so, yeah, we're really small here, but it is fine. So we have this, and, yeah, so we have this quarter, so we have 0.25, so we got 0.25 times VR, you know what I mean? Cool, so we got that. And then over here we got plus 1, this is the 1 kilogram, I almost messed that up, 1 kilogram times VR. Cool, and now over here we got 0.25 times 2 VR. And then lastly we got 0.25 times 3 VR. So now we can solve for, I don't even know if we want to solve for that, but you know, what does that give us if we solve for the velocity? Duh. If we solve for the velocity, we can find the the angular velocity, and then if we okay, cool, yeah, no duh. Okay, because if we actually get the actual velocity of one of these, well, we got the velocity of every little point on here, and then what we want to know is the velocity of this one. So we would want to know the tangential velocity. This is weird. Because the way we have it is that this point is going to move faster than this point. Yeah, oh, that is, remember how I was saying, it's like, oh, this problem would be cool, like if now I don't think the acceleration is going to change, but you do kind of have a lopsided cam, you know what I mean? Because our pivot point's over here, it would be like having a circle, but then having the pivot point right there, you know what I mean? And then you spun it. This point's not traveling very fast, but this point is going hella. Okay, sweet. So that was the deal there. And so what we need to find is if we can find the velocity right here, which is 3vr. If we can get a number on that, what does that say? Well, this had an initial velocity of 0 meters per second, and now we're just solving for this velocity after 1 second right here. So that's going to be the change in, that's going to be the acceleration. So the change in velocity will go from 0 to 3vr in 1 second. So our acceleration of this mass A will be 3vr. Hell yeah. And I think this will be an exact answer using this scenario. If it's not, I'll go back to it, but this video is long enough, and it's the only way that I can explain, well, I mean, currently, it's the best way that I can explain the continuity and turning something into kind of a linear linear mass. I'm just saying, like, hey, the masses are just kind of moving in a linear way. Yeah, that's where, especially if you take this change in time to be a very tiny amount, you know what I mean, then your distances hardly move at all, and everything kind of just moves in a very linear fashion, you know what I mean, things that go, you know what I mean, if they're on circles, they just don't move very much at all. Okay, sweet, I think we got that. So we have, this is 0.25 plus 1, this is 0.5, this is 0.75, and so we're going to add them up. So this becomes 1, 2, 2.5. So we got 2.5 VR is equal to 12.5 newtons. Now this is only the case when this is 1 kilogram, this is 1 kilogram. But for our scenario, we at least got something of an answer. So VR is 12.5 divided by 2.5. 12.5 divided by 2.5, that's 5. So that's 5 meters per second. Alright, hell yeah. And then, and if that's going 5 meters per second, and we only wanted to go, excuse me, like 30 degrees, like for, you know, this thing would have to be really big. I mean, because that's the inside. The inside circle's going 5 meters per second. So after 1 second, if it's only going 30 degrees, can I even do that? Well, yeah. The radius, the radius would have to be 5 meters. Does that make sense? You know what I mean? Because if this is no. If it's going a half a radian, like 0.5 radiuses, then this inner radius would have to be 2.5 meters. I think that's the way it works. Yeah, let's try that. So if this is 2.5 meters, and we have and our tangential velocity goes from 0 to 5. Oh, well, we have that average thing. So we're going, this tangential velocity was 0, and then all of a sudden it's 5 meters per second. So we'd have an average velocity of 2.5 meters per second. Okay, yeah. So now we can kind of yeah, and if we have a velocity of 2.5 meters, what is tangential velocity? That's omega times r. And if we wanted our average speed to be 0.5 radians per second, that's what we want. We want to go 0.5 radians, 30 degrees. We want our average speed to be 0.5 radians per second. We solve for r, that's going to be 2.5 divided by 0.5. So 2.5 divided by 0.5. I don't know why that was so hard, but yeah. No, I appreciate that radians and angular velocity isn't quite intuitive. But yeah, that distance would have to be 5 meters. So I think that is an official check on reality. Because we're going 0... yeah. Is that right? Yeah. Okay, perfect. Because this is 5 meters, and we're going a half a radian. You know what I mean? That's if we measure this out to be 5 and then drape it, we'd go to 60 degrees. But we're only going half that. So we're rolling out an arc length of 2.5 meters. And sweet. And so our average velocity is well, our average velocity for our angular speed is 0.5 radians per second. That's what we want to spell out. Let's see. And we're doing a distance of 2.5 meters per second. No. We're doing a distance. We're doing a linear distance of 2.5 meters. Cool. And so we went 2.5 meters in 1 second. And so we have an average, like just linear velocity of this point, let's say, of average velocity, which is 2.5 meters per second. Sweet. And we started with 0, so our max velocity must be 5 meters per second. And that's what we find. Under all the influences of this, the tangential velocity at this point is 5 meters per second. But that's not even the one we want. We want the tangential velocity right here. And sweet. And this is cool because right now I'm getting kind of confused because, like, hey, if this was on a spindle and then this mass dropped, like, hey, you have to move this entire spindle. Like, that was going to move way slower. But this is, like, I think a little bit supercharged where, like, hey, like, because this is also the scenario, like, if you have this scenario and then you drop it, due to continuity, like let's say after 1 second, both these want to be right here and right here. Well, they can't. You know, you have this continuity that this has to slow down and this had to speed up. So this is a cool property of pivoting rigid bodies that have a center of mass. You know what I mean? Your center of mass is the only thing that will actually travel a normal distance. But that means that the other chunks of mass, well, I think we spelled, I don't know what that last statement, but yeah, we spelled it out true, that, hey, this is going to actually go faster than you think. You know, it might go faster, it's going to whip. And so, I don't know if you'd say that, but there, due to continuity, that's that same thing where, you have a meter stick and then throw a penny on it, and then same thing, when this drops, this end of the stick moves faster than gravity, and then you get a gap to form. And so we see that, I guess I didn't see that aspect of this problem until right now, is that, hell yeah, you just have a huge leverage arm of mass. It's no difference than taking this pivot right there and then just saying, hey, we got a big chunk of mass right there and a little bit more mass right there. And then, so when this drops, due to gravity, both these things want to be in the same location due to the force of gravity, but they can't. This has to slow down a little bit. And then hella, this has to go a little bit faster. And so that's that point that we see. And so now I'm assuming that this thing is going to move faster than gravity. I got to take a little break. All right, hell yeah. So we're back. I took a little break. And, you know what I mean? Where are we in this? We found that the velocity, out at one radius is 5 meters per second. So now we can easily see that 3 times that is 15. So that this is going to be 15 meters per second. And we use kind of that, I'll call it impulse, but the idea that, hey, like what happens after 1 second? And, you have the force of gravity on those masses, And so we did that. You know what I mean? I guess this is impulse. Force times time is mass times change in velocity. But if you just take 1 second, it's very synonymous with F equals ma. You know what I mean? Whatever this number on acceleration is. And so, cool. But then you see how we don't just have one number for acceleration, because all those masses are doing, you know, different things. And so, but we can add up all those masses doing different things, and even the most complicated rotational problems, you know, I mean, hell yeah, just start simplifying it by, you know, making things masses on the perimeter. But I think this one jives. I think this one is 100% accurate. So let's just be done with this video. And so we have that after 1 second, the velocity right here is 15 meters per second. That means that this thing is going to have an acceleration. Acceleration at A is 15, because this point is 15, the string is 15, this is 15. So we have an acceleration of 15 meters per second in 1 second. So hell yeah. So that's going to be an acceleration of 15 meters per second squared. And cool, 10 meters per second squared is gravity. So, you know what I mean, 10 times what is 15? I think it's like 1.5. You know what I mean? So, hell yeah. So, we have 1.5 G. So, yeah. So, this thing's going to experience, so it's just going to, like, just drop out of the sky. So, that's fascinating. We went from, hey, if this was axis right here, it's going to move hella slow. And we kind of, well, it's going to move slower. And we figured that one out. But now, because we actually have this thing just like really leveraged, and it's very similar to this, and yeah, we spelled out the continuity, you know what I mean? And so hell yeah, so I think I'm done with this. Find the acceleration of the weight. Now, what we could do though is, no, I think I'm satisfied, because you could always work backwards from this scenario. Yeah, but we basically said if this chunk of the spindle, these two chunks of the spindle are equal to that chunk, and that's 1 kilogram, and this is 1 kilogram, you know, hey, we found that specific solution, but we didn't find a general solution. You know what I mean? Because, you know, a general solution, yeah, it might get a little bit, you know, too many variables to figure out. So yeah, we just did it kind of for the general solution. But yeah, well, let's see. Okay, we're gonna do it one more time though. Because why are we gonna do it one more time? Because we're going to see if this changes. You know what I mean? Hey, if we actually say this is 2 kilograms and then this is still just 1 kilogram, you know, does anything change? If this number changes, then this number is a function of the input masses. You know what I mean? The fact that this mass is different than that mass, that's going to give you a different acceleration. So, yeah, I think we should at least do that. And so, yeah, I think that's pretty easy to spell out. If this is just twice, all these are gonna be twice. So you're gonna have 1/2, 1/2, 2, 1/2, and then 1/2. And I kind of want to keep, you know what I mean, on this sheet of paper, you know, to have this visual. So now, you know what I mean, gravity is not going to work on that one, and then half of this is going to cancel with this, so we're going to say this is gone, and this is 1.75. And I just do that just to show you, like, hey, the torques on those is going to be the same. So now we're going to have, basically this problem is just like, hey, we have a pivot, and then we have a 1.75, and then we have a half, and then we have a half. And those are the masses that are going to be the under influence of gravity. We kind of went over that. We're going to have a continuity that says these have to be all the same. And so like this velocity has to be 3 times that one. So that's the simple continuity. And I think that is the most straightforward way to understand these problems. Sweet. So let's use F equals ma. And we have a force on this side. It's just going to be the force of gravity on all these. So this is a 2.75. So we have 2.75 times 10, and that's going to be, so F equals ma. We're going to have a force of 27.5 newtons. And then over here, you know what I mean, just because, whoa. Well, let's see. Did we mess up the problem? No, it's very interesting. Yeah, we use that setup just to figure out what the driving forces are. But then we actually have to kind of go back and say we have this original setup of a half a kilogram moving up, and then 2 kilograms moving down, and then half a kilogram and half a kilogram both moving down. So we're going to use, we'll do this one first. This is 0.5, and its velocity is yeah. It's just one. It's just VR. Cool. And then we go to this one. Plus, this is going to be 2 kilograms, and then we have VR. And then we go to this one plus 0.5 kilograms, and we have times 2 VR. And then we go to this last one. That's going to be a half a kilogram, and then we have 3 VR. So let's add these up. This is this will be 1. This will be 0.5 times 3, that's 1.5, and then this is 0.5, and this is 2. So we have 2, 3, 4, 5. So we're going to have 5 VR is equal to 27.5, and so here 27.5 divided by 5. Hey, we get VR is equal to 5.5. So we do get something different. And yeah, that's interesting, and I don't think I messed it up. Yeah. So maybe the equation for acceleration will be a function of these masses. Oh, you know what? And this whole time, did I even include? Yeah, no, we totally messed up because we didn't even include the driving force. This whole time we were just including both these masses. We didn't even include that one. So, yeah, we definitely need to kind of slow down on this problem. And so, yeah, let's draw it one more time. Yeah, no, we got the wrong answer there. Okay, so we have, let's draw this out. You know, here's the inner circle, and here's yeah. So here's the inner circle. Here's the and then, but our pivot's kind of like right there. And yeah, let's go back to saying this is one mass. This is a mass of 1, and this is a mass of 1. So on this pivot, we're gonna have a half, and then you're gonna have a quarter here and a quarter there. Now. On this mass, we're also going to have a half, but then, oh, did I kind of draw it wrong? But yeah, then you're going to have a quarter out here, and a quarter out here, and we don't need that one. Cool. So here's the inner spindle, here's the outer spindle. Okay, but here, hell yeah, you're going to have a mass of 1 due to A. You know what I mean? So those are the masses that we're going to have. And the pivot point, oh, yeah, no doubt. The pivot, this is the center of the spindle, but the pivot point is right there. Cool. And so that's the pivot point. So just like instantaneously, this is going to act as a pivot, and that's going to like have a fulcrum from that location. You know what I mean? Just very briefly. So if that's the case, this velocity, this one's going up, these are going down. Cool. And due to continuity, you know what I mean? Hey, this will be, we're just going to call that VR, VR, this is 2VR, and this is 3VR. Okay. Now due to gravity, the force of gravity, we're going to have, you know, because we're going to add these up. This is 0.25. This is, you know, this won't count. This is 1.25, and this is 1.25. But what we're saying is that due to gravity acting down on this force, it's going to cancel out, you know what I mean, equal and up. Like torque-wise, it's actually going to cancel this one. And that's important because when we use these values, we're going to associate them with their velocities due to that continuity. You know what I mean? So that's the most important thing. That's where if we subtract this one, you know, get this one to 0, then this one becomes 0.75. Cool. So now we have 0.75, 0.25, and 1.5. These are our driving forces. And so that's going to be 2.25. So we're going to have 2.25 kilograms times 10 meters per second squared. That's going to be 22.5 newtons. And we have basically F equals ma. And we're going to say, hey, we're going to run this scenario for 1 second. And after 1 second, this force is going to operate on all these masses. And if they change their velocity, which they will about this pivot point, this one's going to be 3 times the change in velocity, but its mass is you know, is 1, well, it's actually hella now because we're actually including that mass at A. So sweet. So now we can do the problem. So that's going to be the mass, and we'll just start calculating the masses. And now this one's not moving. It's not going to have any change in velocity. So therefore, we don't have to include it as a mass that has change in velocity due to this force causing a mass to have a change in velocity. Cool. So this one is going to be, and the angular, yeah, omega is the same for all of them. But we just know because the omega is the same, that's where you get these equivalences, that this velocity has to be, like this one has to be 3 times this one. You know what I mean? Because if we, yeah, so I think we get that. All right. Okay, so let's just start over here, and we have 0.25 times VR, and then come to here. We're going to have a mass of, so now, you know what I mean, we cancel them out for the forces, but now we can't cancel them out for this setup. So we have 0.25, we have a mass of 1, and then because that's the actual mass that's moving. This is the mass that's moving. So I probably made that mistake too. You know what I mean? So, and this is 0.25, and this will be 1.25. So these are the actual masses that are moving. This one's moving VR. This one's just totally not moving. We didn't include it. And this one's moving VR, 2VR, 3VR. Okay, hell yes. And I'm glad I made some mistakes on this one just because, yeah, it's a little bit heady. Alright, so we have 0.2, that's going to be the mass, times the acceleration, VR. Now we have plus 1 VR, and then this one's plus, I'm sorry, yeah, the mass was 1, and then times VR. This one, the mass is 0.25, but then we got to multiply by 2 VR, and now this one is going to be a mass of 1.25, hell yeah, and then 3 VR. So, sweet, let's see what happens here. We're going to have 3 times 1.25. That's going to be 3.75. So we got 3.75. Here we got 2 times 0.25. That's 0.5. Here we got 1 and then 0.25. So we're going to say, hey, these add up to 4, 5, 5.5. Yep, 5.5. So we got 5.5 VR is 22.5 newtons. Sweet. So we got 22.5 divided by 5.5. And, yeah, sweet. And so we get a velocity of about 4 meters per second for this scenario. And we're going to say that the velocity is 3 times at this point. And so we're going to say the acceleration of A is going to be 12 meters per second squared. So just a little bit more than gravity, you know what I mean, for that scenario. Now, holy Toledo, you know what I mean, we should run through the same scenario again just to see if we could actually do it. And yeah, so we're going to put that aside. We're going to have, here's the radius, here's the pivot, here's the center of the first spindle, you know what I mean? And then here's where A would be. And so now we're going to say that this is 2 kilograms. So we're going to say, hey, this axial spindle is 1. And then so we're going to say half of its weight's here. So we're going to say, hey, that's a half. And then we have a quarter on the edges. Now for this one, same thing. We're going to say it's a half. And then we have a quarter on the edges. Now, is this just the same problem we just did? You know, did we already, in this one, did we make this 2 kilograms? Yeah, no, I guess we did. So what's the difference? We want to actually change this up. So let's call this 4 kilograms. And so here's the pivot, here's the center of the circle. Hell yeah. So kind of here's what we have. This thing's going to be 2 kilograms. So we're going to have 1 kilogram here and then half on the outsides. There we go. This looks better. And then for this spindle, we're going to have 1 kilogram here and then half on the outsides. And again, what we're doing is we're taking a disc and just saying its mass is going to be 2 right there. And then if it's a mass of 1 kilogram, we're going to have a half and a quarter and a quarter. If it's a 2 kilogram disc, we're going to have 1 and then halves. So these add up to, you know, 0.5, 0.5, 2, 0.5, and 0.5. Okay, so now we have the force of gravity on these masses. Not on this one because it's on the pivot. And this one's down, and then and that kind of acts, you know, that kind of lifts this side. So we're going to say, for that sake, for the total force, we're going to say, hey, this is none, and then this is going to be reduced by 0.5. So we got 1.5, 0.5, and 0.5. And if this is the masses, times 10 will be the newtons. So we have 15, 5, and 5, and we're going to have a total of 25 newtons. 25 newtons. Now, when we go back and actually do the problem so we're saying force is equal to mass times acceleration. We're going to have a driving force of 25 newtons. In our other problem, so I feel like, yeah, no doubt, we already messed up. Because I always forget that we have this mass A right here. And so we're going to have 1. You know what I mean? We're going to have this half plus 1, and that's going to be 1.5. So now we have 1.5, and now we have 15 newtons there. So we're going to have 35 newtons. Hell yeah. So now we're back on track. So we have this 35 newtons. We're going to say this operates for 1 second, kind of like that impulse. So each of these masses are going to change their velocity. Well, here, let's figure out what these masses are. So this mass is going to be 0.5, 0.5. This mass is 2, 0.5, and then 1.5. So these are the masses that we're going to use. This velocity is VR, none, VR, 2 VR, and then 3 VR. Okay, now we're on a roll. Okay, so we have 0.5 times VR. this one is not moving, so this force is not generating any change in velocity of that mass. Hell yeah. And then so this one is going to be a mass of 2 times VR, and then this one is going to be a mass of 0.5 times 2 VR, and then this one's going to be a mass of 1.5 times 3 VR. So let's see if we get the right answer, you know, or similar. I don't know if it's going to be different, that's all. So we have 3 times 0.5, that's going to be 4.5. Okay, sweet. So we got 4.5 there. This is going to be 1, and then we got 2 and 0.5. So this becomes 5, 6, 7, 8, and we got 8. VR is equal to 35, so VR is 35 divided by 8, and we get 4.375 is equal to VR, and then times 3, so our acceleration is going to be 13.125 meters per second squared. So now this is kind of, it's alright, but it just shows that I've developed a system to find the acceleration, but only given, you know, what these masses are. And I think, yeah, that's the interesting thing with this problem. I kind of solved it more because I've actually chosen masses for, like, I've chosen that this is a certain mass and then this is a certain mass. Where for their problem, they just said, hey, this is just I, get on with life, for the whole unit. And I think that is just a disservice because it doesn't even allow you to kind of figure out like what mass is moving, you know what I mean? And so yeah, so I think that will be a decent place to call it. Just knowing that I think my setup is fairly legit. Now I'll probably do a second video on this of actually using the normal equations, you know what I mean, and just like the idea of it would be, you know what I mean, we have that pivot, and then we have most of the mass outside here, with these circles, with the pivot being right there. So what we're going to have is we're going to generate a torque, and we have this idea that torque is I alpha, but guess what? This alpha is I change in omega, change in time. But again, let's say change in time is just 1. You know what I mean? 1, and then cool. So we kind of have this value of like torque is equal to I change in omega. Same thing of force is equal to mass times change in velocity. Now it is torque times time. If we did this, then we had I change in angular velocity, change in time, and that's the definition of angular acceleration. And then you just multiply by change in time. So then you get this equation. So then you could figure out the change in you could figure out that you're going from 0 to some radians per second after 1 second. And then due to continuity, if this was your pivot, this one's going to be going 3 times the speed. Or if you know your omega, then you could figure out your tangential velocity out here. And if you knew your tangential velocity, well, you had 0 tangential velocity starting, and then after 1 second you have this. So acceleration is going to be that tangential velocity. You know what I mean? Per 1 second. And heck yeah. And and so if we knew omega, then omega times that radius, which for our case that would be it would be the radius from this pivot point. So that's going to be 3r. So we would have omega times 3r, and that is going to give us our tangential velocity. So after 1 second, that would be our acceleration. So our acceleration is just going to be omega 3r for this problem, I would assume. But you don't know how to find omega until you actually sum the torques, and the sum of the torques is equal to the moment of inertia. Yeah. So anyway, and these equations I'm just not super strong on until I definitely develop a fundamental understanding of those. So we're just going to, hopefully I did it right, you know what I mean? And we're just going to come back to this problem later with that format. But heck yeah, so I think I'm pretty satisfied with the way I solved it. We used, you know what I mean? Yeah, I think you get it. Yeah, we use kind of linear momentum with continuity, and then hey, we even brought in this term omega for sure because it's going to be, you know, in a line and stuff, and we showed how that worked. But heck yeah, and you know, I mean, it's not a big deal that I just don't know how to solve that. There'll be a time where I will be able to. And most people, this is where they spend all their time, is just, hey, getting the equation and figuring out the problem. But no one spends the time doing this, of just like, hey, how do you take a problem and make it into bite-sized chunks that are actually, where you can see the steps, where you can take the leap of faith, you know, every time, be like, hell yeah, there's a force on that mass. But due to continuity, you know what I mean, they can't fall at the same time, and there's going to be an angle, and then, you know, blah, blah, blah. And so I think we did it. So thanks for joining me on this one, and guess what? That's a video.